Well, hello and welcome YouTube, Mr. Robinson back here with yet another brand new exciting video, all math-based of course. And as always, it's an honor and a privilege to be serving you today, as it is every day here in my virtual classroom. Step on inside, we are in section 6.4 of the Big Ideas Math Integrated Math 2 textbook, finding medians and altitudes of triangles. Now so far we've done some things within proofs that have to do with the theorems that we're using so far and things within triangles, yada yada, constructing proofs in general, which has been great. That was section 6.1. Section 6.2, we were doing perpendicular bisectors and angle bisectors of triangles, therefore learning some theorems which could apply in anything that we do, or at least within that section, the scope of it. And in 6.3, we did bisectors of triangles using perpendicular and angle bisectors, to find the circumcenter and the incenter of triangles. And that was a long section. I had some trouble with that section, even doing some of the later problems. Apologies if you started to do some of those later ones. They were toughies, at least on the technological level, doing it on the computer, using compass construction and stuff. It was a bit. We'll see how this one goes, where we have, once again, medians and altitudes, and we are going to be finding what's called the centroid of a triangle and the orthocenter of a triangle. Hopefully a little more drill and kill, but we do have, I believe, 51 problems, if not 54 or something. We'll see how that goes. But without further ado, we will start with the lecture portion of this. If you want to find the problem set itself, go down to the timestamp below. You'll see where those problem numbers are and click on those timestamps or tap it with your little finger or your thumb, and then you can go and navigate to those. Otherwise, let's go ahead and start a lecture. There's a PDF of this whole section down below in the link, in a link as well, I should say. Okay, let's go. Let's find out what they want to do. Use medians to find the centroids of triangles. Use altitudes and find the orthocenters of triangles. Now, I'll let you know before we begin that, guys, this is a lot of different words, like, circumcenter, incenter, centroid, and orthocenter. And I get if you don't remember them. Full disclosure, I don't always either. It just happens. And over time, I'd say circumcenter, incenter, I remember a lot more, because their word has to do with circumscribe and inscribe. And when you see where they go in the triangle or why they're made, it makes a lot more sense. These ones take a little bit more. Furthermore, some of them don't quite have as much of a relatable purpose with regard to circles as circumcenter and incenter do. So hopefully you get to know those two based off their meaning, their understanding, and what they do, and use learn these ones, study these ones enough so that you remember them when you have to, basically. But let's practice them here. A median. Now, we should know the word median and altitude in general. Those are ones that you're not like, what does that mean? A median of a triangle is a segment from a vertex to the midpoint of the opposite side. So it's very specifically is this segment here from point B to point F. F is the midpoint of segment AC. D is the midpoint of segment AB, and you draw from C to D, and you draw from A to E, where E is the midpoint of segment BC. You see the congruent marks that show that. The three medians of a triangle are concurrent. We noted that meant that they will all meet at the same place. They'll all intersect together. The point of concurrency is called the centroid, and that is inside the triangle. It should always be inside the triangle for medians, because medians are always drawn inside the triangle. These are not angle bisectors. This angle does not necessarily bisect that angle. In fact, I believe it only would if it's an isosceles triangle and if it's drawn from that one, or you know what I mean. So that's not an angle bisector. It's a segment bisector. Okay. I read that part. Okay, here's your centroid theorem now. When you draw your centroid based off your medians, the centroid of the triangle is 2/3 of the distance from each vertex to the midpoint of the opposite side. The medians of triangle ABC meet at point P, and AP is 2/3 of AE, BP is 2/3 of BF, and CP is 2/3 of CD. Okay, so what does that mean? Look at AP. This length is 2/3 of the entire length there. So this is 2/3 of it. This is the other 1/3. 2/3 and 1/3 of that entire length. This guy is 2/3 of that guy, of the whole thing, and this guy is 2/3 of that whole thing as well. So it is legit broken up into thirds, where P, the centroid, breaks those parts up. Okay. You can find a proof on bigideasmath.com, apparently. I haven't done the proof myself before, and I'm not sure how the proof works. I think you have to deal with areas and stuff to then determine heights of triangle. I'm actually not sure. I haven't tried it. So, but there's a proof on there, I suppose, if you want to go ahead and find it. Okay, finding the centroid of a triangle. This actually would be a little bit easier than some of the other ones you did. Now, they require some of the same bits. Notice this compass construction, and if you did compass construction with me before, you saw when I would use these two endpoints, like this C and this A, and I would create a perpendicular bisector by drawing arcs a little longer than where the midpoint would be, and find their point of intersection and draw a line through them. Now that is technically the perpendicular bisector, but we don't need the actual line, we just need where they intersect. They intersect at F, which breaks it up into two congruent points. So that's what they're doing. They're drawing perpendicular bisectors so they can find the midpoint. That's the concept of these. You draw 3 of those, and you draw segments from one vertex to the opposite side, where that midpoint is, another vertex to that point, another vertex to that point, all segments. Boom, you should find its centroid by constructing it. If they ask us to do it, I'll happily do it for like one problem or two, for a couple problems, but I hope it's not the crux of a bunch of things that we do, because they show you how to do it here. How do you use the centroid of a triangle? Well, there was the centroid theorem. They say in triangle RST, point Q is the centroid. That does mean that these are broken up into congruent parts, by the way. U, W, and V are midpoints of the triangle segments. And the length of SQ is 8. They want you to find QW and SW. Well, QW should be, SQ is 2/3 of the entire thing, which is what they're saying. SQ is 2/3 of this, so 8 is therefore 2/3 of that. Now, how do they get 12? They multiply both sides by the reciprocal 3/2. You multiply by 3 over 2 on both sides. 3 divided by 3 is 1. 2 divided by 2 is 1. Those cancel, right? We don't want to say divided by 2/3 if we can say multiply by its reciprocal. 8 times 3/2. 8 times 3 is 24. 24 divided by 2 is 12. Or 8 divided by 2 is 4. 4 times 3 is 12. I'll use either or. If the answer ends up being a decimal, maybe we can write it as a decimal, which isn't terrible because it's just like a 0.5 value. So we can use that. We'll see if they give us that. Now, the 4 should be either 1/3 of this or the difference, as they show it, the difference between 12 and 8, right? Because if this is 8 and the whole thing's 12, then 4 is just the little guy through subtraction. Finding the centroid of a triangle on a graph. So find the coordinates of the centroid of triangle RST with vertices 2, 1, 5, 8 for S, and T is 8, 3. They use the midpoint formula to find midpoints because that's the whole idea, right? If you can find a midpoint of this guy and, oh, they don't even have to find the midpoint of a second one because they know the relationship's 2/3. But if they find the midpoint of one of them and draw the segment, you know the centroid is somewhere on here. Now you could find a second midpoint and then draw it through there and then connecting it would find its thing, right? However, what they also go for is the 2/3 argument. They find out that this whole length is 1, 2, 3, 4, 5, 6. The distance of the whole thing is 6. So 2/3 of 6 is 4, and it would be 4 down from the vertex point. If you were curious, and how would I know if it's 2/3 up from this point or 2/3 down from this point? Based on what we saw in the theorem, it's 2/3 away from the vertex point, not from the midpoint. The midpoint is 1/3 away from the centroid, like that. So you could draw 2 different intersecting points. You could use the 2/3 thing. If they are kind, they will give you 2/3 values that are not big fractions, at least in the beginning. We'll see what they do after that. But that's where that begins. So the coordinates are 5, 4 for the centroid. Okay, there's some it's monitoring progress. I'm going to leave that. I'm going to leave it to a problem set if we have them. And then let's talk about altitudes. I've used the word probably quite often, and they're telling you something over here I think I want to read later. It has to do with, hopefully, with area, yeah. An altitude is basically you drawing something perpendicular from a vertex. Altitudes do not have to be in there. Oh, right here. Altitudes do not have to be inside of the triangle. So the altitude from point Q goes down to segment PR and makes a right angle. It's perpendicular to it. And then Q goes straight down to the extended version of side PR like that. And this is actually outside of the triangle. You can see the triangle is all in black right here. And this is on the outside. And altitude is perpendicular, period. And that is important, because altitudes are a way of constructing some sort of height. And this is where I want to talk about area. I'm sure I've brought this up before. In the area formula for a triangle, area is 1/2 base times height. You can use the length of any side for base B. The height of the length, the height h is the length of the altitude to that side from the opposite vertex. So if I want to find the area of this triangle, I could use this as my base. It must be a side length, but this must be the height. It is more of an abstract value. It's not necessarily a side length. It's just a visual kind of thing. The height is perpendicular to its base. If this is my base PR, this height here is that distance right there. Therefore, assuming these PRs were, I have no idea, assuming these PRs were the same length, it looks like this height's the same length. If these PRs are the same length and this height's the same length, these triangles have identical areas. These two right here would have identical areas. It's 1/2 base times height. So anyway, height is always perpendicular to the base that you use, point blank, end of story. That being said, if this was my base here, my height would be this perpendicular distance essentially right there. You'd find that if you could. Okay, let's keep moving forward on this and talk about orthocenter. The lines containing the altitudes of the triangle are also concurrent. Very cool thing about triangles with all this concurrency. If I draw an altitude from C, from B, and from A, they should all intersect at the same point, G. This point of concurrency is the orthocenter of the triangle. The lines containing AF, BD, and CE meet at the orthocenter G of triangle ABC. Excuse me. Let's see if they talk about, I don't know what they're going to bring up next when it comes to these things, but I'm going to say more if they don't. As shown below, the location of the orthocenter P of a triangle depends on the type of triangle. An acute triangle, orthocenter is on the inside. A right triangle, the orthocenter is on the triangle. It should make sense that it's actually part of the right angle itself, because altitudes from this point and that point will go straight into the right angle. So the orthocenter is right there. This is the perpendicular, or excuse me, no, this is the altitude right here, which is kind of irrelevant except to show the altitude draws to that point itself. And then here the altitude, remember the triangles are in black. The triangle is in black right here. So this altitude from this point draws to there. Remember, it's this side extended. It draws to there. But it keeps going through, keeps going more. This altitude goes to that extended side right there, but it keeps going more. And this altitude is on the inside, but we extend it on the outside. So orthocenter's outside of the triangle, like so. Now they're jumping straight into examples. So what I wanted to mention is this. Unlike a circumcenter, which has certain like measured relationships, and an incenter and a centroid, all of those seem to give you a little bit more that say the circumcenter is equidistant to all the vertices of the triangle. The incenter is equidistant to all the sides of the triangle, and the orthocenter is 2/3 the distance from the vertex of the triangle to its midpoint, stuff like that. Excuse me, centroid. The orthocenter doesn't have any of those relationships necessarily. So the kinds of questions that they ask, I don't know what they'll be asking. Here they ask you to find the orthocenter. We maybe have to construct them and such, but there's no mathematical relationship that's necessarily a guarantee through a theorem or anything like that. So we'll see what they ask you to find with them. I don't know. But finding the orthocenter here is on a graph basically by finding through the vertex the opposite reciprocal slope. So we have x, y, and z is these 3 points right here. We graph them, and then we find an equation. Find the coordinates. They want you to find the coordinates. Okay. So you find an equation of a line that contains the altitude from one to the other, etc. Basically, you want to find opposite reciprocal slopes. If we know that this yz has a slope of -1, its opposite reciprocal is +1. So from x through here, we go up 1/1, etc. And then over here, we have an xz slope that's 0. Its opposite reciprocal should be undefined, a vertical line. So we draw a vertical line from y through there as well. 2 lines should be enough to find that one point of intersection. Remember, it is concurrent, so any 2 should be fine. It's not like a 2/3 relationship this time, so the orthocenter is right there if you draw it correctly at -2, 2. They asked for full they didn't ask for full equations on this. They said find the coordinates of the orthocenter. So it's not so much about y equals x plus 4 and x equals -2 as equations of lines, unless you think it helps you find it mathematically, or unless they request it. So I'd probably just go straight for just drawing them. Or if they intersect at an approximated points. That's why I said solve it algebraically is probably one. But -2, 2 seems to be that orthocenter. In an isosceles triangle, the perpendicular bisector, angle bisector, median, and altitude from the vertex angle to the base are all the same segment. I've kind of mentioned things like that before. I think we started to bring it up a little more in the last section, that here's your isosceles triangle. These are both the same. So this is the altitude. Boom. But it's also the segment bisector. Boom. But it's also the perpendicular bisector. Boom. And then it's also, what's the last one they said? Angle bisector. Whoopsie. It's also the, where'd I go? It's also the angle bisector. Boom. Those are all the same in an isosceles triangle. There are a lot of ways we could prove that one playing with it. It's just about once you find congruent triangles, you have CP-CTC going on that shows all the other parts are congruent. You can do that using anything. As long as you have a given that it's one of them. Given it's a segment bisector, prove that it's all the others like that. So they're going to show that. Prove that the median from the vertex angle to the base of an isosceles triangle is an altitude. Let's prove that They know it's a median, so D is the midpoint of, therefore these are congruent. And we're also given it's an isosceles triangle, therefore we know those are congruent. So let's see what they do. They're going to obviously use the reflexive property here in a moment to show that's congruent. So let's see. Given triangle ABC is isosceles with base segment AC, and segment BD is the median, prove that BD is an altitude. So legs AB and BC of an isosceles triangle, of isosceles triangle ABC are congruent. So here's the first. Wait. They are the, okay, they're not, okay, they're just saying they're congruent. Okay, so they're congruent. That's the first guy. CD is congruent to AD because BD is the median of AC. That's the definition of a median. It's going to intersect at the midpoint, break it up to those parts. So I guess you don't have to say midpoint. BD is congruent to itself by the reflexive property. So these two triangles are congruent by side, side, side. Therefore, so now we know these two triangles are identical in nature. One's just a reflection of the other, right? Therefore, all their corresponding parts will be congruent. Now, the corresponding part we need to be congruent is this angle congruent to this angle. But there's more. We need to show that it's an altitude. So these are congruent because corresponding parts are congruent, but they're also a linear pair. That's just by the nature. It says it's a linear pair. I mean, by definition of a linear pair, that this is a straight angle itself. It's a segment. We understand that. So it's 180 degrees. If they are congruent to each other, see, I would have actually said more. If they're congruent to each other, then they have equal measure. If they have equal measure in a linear pair, then each of them are 90 degrees. If each of them are 90 degrees, then they're right angles. If they're right angles, then it's perpendicular. So I would have probably said more in terms of the 90 degrees thing. They just say they intersect to form a linear pair of congruent angles. Therefore, I guess that's maybe a linear pair congruence theorem. It must be a way to say the same thing I mentioned. Okay, let's keep moving down and look at something they want to tell us. Okay, so here are the 4 different kinds of centers. They're just showing you again. Let's recap. Concept summary. Probably the last page. Perpendicular bisector is from the segment, from the side itself. It is the point for which this altitude intersects through. It's the midpoint. It reveals a circumcenter when you find all 3 perpendicular bisectors congruent. Circumcenter is equidistant to the vertices of your triangle. Boom, boom, boom. You see that right here. Angle bisectors is the segment, or line or whatever, which divides the angles into 2 congruent parts. When you find their point of concurrency, you find what's called the incenter, which is equidistant from all 3 sides. Equidistance meaning shortest distance, the one that's perpendicular to the sides. You could draw an inscribed circle into there. A median is a segment from the vertex to a side opposite, which intersects at the midpoint. Unlike a perpendicular bisector, which is just something that goes straight up, this goes literally to the vertex of the side opposite, like this. All 3 of them are concurrent and meet at the centroid. The centroid draws things so that you are 2/3 the distance, so that this length from vertex to centroid is 2/3 the length of the entire median. So 2/3 of that, 2/3 of that, and 2/3 of that. And then the orthocenter is where you draw all 3 altitudes, not necessarily perpendicular bisectors right there. That didn't bisect this side over here. All 3 of those will be concurrent as well. But there's no mathematical connection relationship like all 3 of those have. So it's a name. It's a name. And ortho, here's a way that you could remember this one. I guess you'd have to know the word. The word orthogonal. Orthogonal is something similar to perpendicular. The way that I was taught back in high school in the day was orthogonal can be perpendicular in any sense. It can also mean in 3D. Like from a plane, this pen is orthogonal to the plane. I don't know if that's the way that it's supposed to be meant, but it can be perpendicular in any sort of dimension sake. All right, guys, we're going to move on into the vocabulary and core concept check, numbers 1 and 2, and then we will do the problem set. Are you ready? I am. Let's go. Name the 4 types of points of concurrency. Which lines intersect to form each of the points? So, that was just named in the last one, if you just saw those pages in the concept summary. The first one we'll use is called the circumcenter. That is made by the intersection of the perpendicular bisectors of the triangle. I'm just going to go ahead. I'm going to keep it kind of short. I'm just going to say that. Okay. Next one is the incenter, which is made from the angle bisectors of the triangle. The third one, part of this section, is the centroid, which is made by the... Why did I capitalize this and not that? Centroid, which is made by the medians of the triangle. And then the orthocenter, which is made by the altitudes of the triangle. Excuse me. It's probably a good review to have and look at and recall. And like I said, if I went off, after recording this video and teaching it to my kids and having the chapter and final and stuff like that, if I go next year and have to reteach this, I'm going to have to look up some of these again, probably. I'll go like, which one's the centroid and all that? I think by process of elimination, I could figure out that the centroid is the medians by knowing all the other ones based off what they do and where they meet and stuff, maybe. All right, complete the sentence. The length of a segment from a vertex to the centroid is blank the length of the median from that vertex. So vertex to centroid, we're talking about the medians all intersecting and such. That's 2/3 of the length from the median, from that vertex. The median's the entire thing, and then 2/3 of the median meets at the centroid from the vertex. That's the fraction we're going to use. All right, guys, we are going to go into the problem set itself. Get ready. It is problem numbers, let me see, 3 to 54. So we have more than 50 problems to do. I'm ready. Are you ready? Let's go. In exercises 3 through 6, point P is the centroid of triangle LMN. Find the length of PN and QP. So that's true for each of them, right? I wonder if I always wonder this, if I should copy the diagram over or if I should just point to the one that is there. I think I can point to it. So P is the centroid. Find PN and QP. When they say the length of QN is 9, so the entire thing here is 9, like that. I'm going to go ahead and write that as well. QN equals 9. And they want to find PN and QP. Now, PN is going to be 2/3 of QN. QP will be the difference between those. So PN is 2/3 of QN. I guess I don't need that in parentheses. I'll need this in parentheses, though. 2/3 of 9, which is 6. I don't know if I need to go into the calculation as to why that is. You might know that one. We'll do ones that are more dire if needed. Now, PQ, or QP, the way that they say it, QP, you can either say it's 1/3 of this thing, or make it easier for 1/3 isn't that bad. You can do the difference between these two, kind of the way that they said it, QN minus PN, which is 9 minus 6, which is 3. So that's the length of those two parts individually. So therefore, this is 6, this is 3. Like that. That's number 3. Number 4. QN equals 21. Now, P is always the centroid. Never mind. I was going to say something different. All right, QN is 21. I mean, more of the same, right? It's always a 2/3 proposition. Nothing's going to change there. But if this is 21, entire thing, then we're talking about getting PN, which is going to be 2/3 of that. Okay, PN is 2/3 of QN, which is 2/3 of 21, which is 14. Now, if you're unaware again of how I'm doing that, I'd rather you do the division first. 21 divides by 3 to get 7. 7 times 2 is 14. Easier work with smaller numbers than larger numbers. That would also help answer what the next one is. QP should be 7. Let's double check that through subtraction. So we're going to get QN minus PN. After this, I'm not going to write that actual subtraction if I can help it. So that's going to give you 7. So whole thing's 21, but here we got 7. And here we got 14. Good little practice on those guys. Number 5, QN equals 30. QN, once again, the entire thing. It looks like on all of these, QN's the whole thing. So I'm not going to write the little formula within. I'll just straight up substitute. But QN equals 30. Okay, can we do this without drawing anything? Look at where QN is. PN is going to be 2/3 of it because N is at the vertex once again. So PN is 2/3 of QN. 2/3 of 30. 30 divided by 3 is 10. 10 times 2 is 20. So 20 units. QP will be 30 minus 20. Find that difference and you get 10. That's number 5. And number 6, QN is 42. And once again, you just kind of want to look at the diagram and make sure that everything is the way that you expected it to be. Like QN is the entire thing. Pn will be 2/3 of that, all that. So Pn it's 2/3 of 42. 42 divided by 3 is 14. 14 times 2 is 28. See, on this one, you might say, oh, I want to do 42 times 2. You can. That's 84. You got to take 1/3 of 84, and that might take a second, divided by 3. QP should be 42 minus 28, which will give you 14. So using that process, knowing it's a centroid, knowing what it does is all good and gravy. Let's move forward. Numbers 7 through 10. D is the centroid. We're going to find the lengths of CD and CE. Now this time, I assume they're going to do something different. Yes. DE being 5 is just from the centroid to the side opposite the vertex. This is the 1/3 of this whole thing. So we don't know what the whole thing is yet. So what would be nice to do is probably find that whole thing first. Oh, no, you know what? Either or works. This is it's totally up to you as far as how you want to work this thing out. Let me do it differently one way versus the other way, things like that. So like this, for example. This is, because I don't want to get too deep into this. This is 1/3 the entire length, and this is 2/3 the entire length, CD. If CD is 2/3 and DE is 1/3, then CD should be twice the amount of DE. In fact, I probably should have done that with all of these. Half of 20 is 10, half of 20 is 14. I didn't notice to mention that. Half of 14 is 7. You can divide them by 2, subtract them, or take 1/3 of the entire thing. So many different ways you can do it, and I think that's where I'm going to kind of hit this, is I can do this a lot of different ways. 2 times 5 is 10. So this guy, not the whole thing, just CD is 10. So now the entire thing CE is what we got to find next. So CE, again, you have options. You can triple 5, or you can do 5 plus 10. It's going to be CD plus DE. CD plus DE, which is 10 plus 5, or 15. So the entire thing there is 15. That's one way of going about them. Great. Let's go with DE being 11 on number 8. So now we got 11 for this guy, with D being the centroid. This time let's go for the whole thing first. Let's say that CE, the entire thing, that should be triple this 11. Okay, hold on. Maybe you don't know that, but you might know. Let's see, how do I want to say this? I'm sorry. CE, 1/3 of CE. 1/3 of CE is DE. So 1/3 of CE is 11, and then you multiply both sides by 3. So it's tripling that 11, right? I'm kind of using more of what you knew before and how we use that after. So CE is 33, the entire guy. So how can you find CD? You have options. You can either take 2/3 of 33, or take the difference here once again. CE minus DE, which is 33 minus 11, which is 22. I'm just kind of providing all those options. I think it will be kind of important depending on when we have to use graphs and what kind of way we have to look at the problem based on the numbers of the points that they give you. I don't know. Maybe it's good to look at all those. So DE is 9. So the short guy is 9 here, right? CE should be triple that 9, which is 27. Now let's do it that other way. Let's say now CD is going to be 2/3 of CE, which is 2/3 of 27. 27 divided by 3 is 9, times 2 is 18. So we got those in kind of a different light on number 9. And number 10, DE is 15. You can see that kind of long guy right there, but not quite as long as everything else that's there. Let's look at DE is 15. Let's do the doubling thing again. Let's say CD. CD is 2 times 15, which is 30. And let's do it this way. Let's say CE, 2/3 of CE is CD. So 2/3 of CE is 30. I know you could do 15 plus 30, I'm well aware. And you can multiply both sides by the opposite reciprocal, which is 3/2, like that. So CE 30 divided by 2 is 15. 15 times 3 is 45. So you get 45, which is the same thing as 15 plus 30. Just kind of giving you an understanding of every single thing. It depends on what they ask you and what's going to be fastest for that. Okay, let's keep moving forward. Let's look at number 11. 11 to 14. Point G is the centroid of triangle ABC. This time I feel probably more compelled to copy this down. Depends on what they want. Hold on. Let's get the diagram. Let's get the diagram. Okay. G is the centroid. BG is 6. That's labeled. AF is 12. That's labeled. AE is 15. Not labeled. Where is it? AE is the entire thing here, 15. Find the length of the segment. So whichever one's given. They want to find the length of SFC, what that one is. Notice how I'm drawing it without a bar, by the way. They draw the bar FC, but I won't say something like FC is 7. We don't do it like that. We would actually do this. You would say the length or measure of segment FC equals 7, something like that. By the way, that's not the answer. I'm just saying that this is what you would do or this is what you do. So I'm going to do it without the segment bar above it. Okay. Full disclosure, I think I'm going to answer all this before writing them down. Okay? I want to actually just navigate through this thing the best way I can. For example, AF is congruent to FC. If this is indeed a centroid, then these are drawn, then these are the medians that are drawn. That means that these are going to be congruent. If this is 12, that's 12. 6 is 2/3 of this entire thing for BF. Okay, so I won't do anything if I can't do that. So BF is going to be, I don't know, bigger. We also kind of noted that this is twice that amount. I think that was worth noting last time. So if this is 6 and this little length is 3. They also told you that AE is 15. So 2/3, I feel like I should be waiting to do all these, but I just want to label them in case I got to go down lower. 2/3 of 15 is 10, and 15 minus 10 is 5. So we know all of those lengths now. Let's see if we can answer any of them based off that. FC, it probably does. FC is 12. FC is 12. It's the same length as AF, which is 12. Number 12. I'm just going to go straight shots through these. Length of BF. BF is going to be 9. Now, the way that I got it was by finding this 3 being half of this. So I could do that. I'm guessing the way that they'd expect you. Well, not expect. There's more than one way. I did the 6 plus 3 thing, but how to get the 3? It was half of that. You could also say that BF is 2/3. Excuse me, BG. Let me do that again. 2/3 of BF is BG. So 2/3 of BF is 6. If you multiply both sides by 3 halves, you also get that same 9. 6 divided by 2 is 3. 3 times 3 is 9. BF equals 9. Once again, you could also do the other guy. AG. Looks like I wrote it. How did I get it? AG was 2/3 of the 15. So number 13, AG, is 2/3 of AE. Length AE, and AE is 15. AG is 2/3 of 15, which is 10. So there was that labeling. And then number 14, the length of GE. I wrote that as 15 because I said, or 5 because I said 15 minus 10. So 14 GE is AE minus AG, which is 15 minus 10, which is 5. Okay. Might have overdone some parts. Don't know. Looks pretty good. In exercises 15 to 18, find the coordinates of the centroid of the triangle with the given vertices. I got to go to my graph things here. So I guess we're going to draw 4 different graphs, huh? All right, number 15. Find the centroid. So we have A as 2/3. Excuse me. A is 2, 3. B as 8, 1. And C as 5, 7. So A, 2, 3. B, 8, 1. C, 5, 7. A, B, C. Okay. Let's go. Let's find a centroid. Now, the example that they gave was a pretty good one. Not a good one, but they showed a good way of going about this. Remember, if I can draw any two medians, then the point of intersection should be concurrent with the third median. So I wouldn't need all three. I would only need two. However, you can also get away with only drawing one of them if you find its midpoint and find 2/3 the distance from the vertex. So that should just be enough. For example, I can find the midpoint of segment AB because I'm drawing it. And I don't know, maybe what I'll do, I'm thinking about it. I'm thinking, should I ever go without drawing them? Or like basically how am I calculating it? Because they show you the calculation of the midpoint, right? My midpoint of segment AB is this guy right here. How do I know? It looks like it. No, really, how do I know? I'm going down 2 and right 6. Down 2 and right 6. So down 1 and right 3 would be half those distances. So this would be the midpoint of segment AB. So its midpoint is there. Therefore, the median drawn from C is going to be this guy right here to the midpoint. It's vertical in the sense that it just goes straight from one point to the other. It's not anything like an altitude, but that is one of the medians. That's the median from C to segment AB in this triangle. Now, the centroid would be within this guy right here. Now, this length is what's important because whatever that length is, let's call this length, or let's call this point D. How about D? The length of CD is 1, 2, 3, 4, 5. So the length of CD is 5. Well, the centroid, if centroid is there a specific point they say? No. The centroid point will be 2/3 of that distance. 2/3 of 5 is 10/3. Now, this is kind of a little weird, right? 3 and 1/3. That's a little bit weirder to talk about mathematically. And I'm giving this value so we can actually work that out. If I go 3 1/3 down, 1, 2, 3 and 1/3, I get this centroid right here. We'll call it P. P. Now, P is 3 1/3 down from C. The X value is 5, but the Y value seems to be 1, 2, 3, and then 2/3. Because this is 1/3 down from here and 2/3 up from there. So if I can write as 3 2/3, P, the centroid, is at 5, 3 2/3. I could also write a fraction version. I don't think it's best to approximate it, like round it as a decimal, but I could also say 5, 11/3. That would also be 3 2/3 like that. Either or seems fair. So the very first example that they give you doesn't have whole numbers, integers, which is interesting. And also, that would also make, if I drew two different medians, then I would have had to use more math to confirm that that's indeed the location. It's 3 2/3. So I know it's not 3 3/4. I know it's not 3 1/2, because then I have to trust more of my drawing, which is not ever a good thing to do. Even if it's a perfect drawing, I shouldn't trust it by eyesight. I got to trust it more so mathematically, and I think I did it there by doing 2/3. All right, number 16, we get F at 1, 5, G at -2, not -3, -2, 7, and H at -6, 3. Let's go and label those guys. We got 1, 5 for F, -2, 7. This is going to be a smaller triangle. And -6, 3. Kind of. F, G, H. All right. Okay. Let's find a midpoint. I like to kind of hunt for which looks like the best, most integer-like midpoint. I think it's going to be this one right here, and that's going to be nice because it'll be a horizontal line. I can count those distances. I'm really seeking those. So I'm going to find the midpoint of segment GH. I believe it's right here. If you count, we go rise 1, 2, 3, 4, run 1, 2, 3, 4. So half is up 2 over 2. Up 2 over 2 gives me that midpoint. If you don't know how to calculate that, you can also average your x's, average your y's. Take a look at some of the examples that were typed out before. But I have the graphs visual. I'm going to use it as long as it seems to make sense. Let's use that midpoint. Let's call it GHI. I won't use I. I'll use J. point is J, all right? J is being that midpoint. It is at -4, 5. Is the point itself important? Sort of. It depends on counting measures, how well you're able to count something, or if you have to use more math on it. This one might be another fraction hiccup. Let's take a look at what this distance is here, because this is the median. We need to do 2/3 of the way from F to J. And I need to call it FJ, by the way. This length is 1, 2, 3, 4, 5. It's also 5 again, or -5. I mean, that doesn't really matter. But the length of FJ is 5. And 2/3 of 5 is, once again, 10/3. 3 1/3. So we got to do 3 1/3 over this way now. 1, 2, 3 1/3 is this centroid right here. Also P, like before. Now, this one's easier to calculate because this is at -2 1/3, comma, and up 5. So that point P is at -2 1/3, comma, 5. Because it's 3 1/3 away from F. F is at x = 1. And that would also be, instead of -2 1/3, you say -7/3, comma, 5, like so. Either of those should work out. Okay, giving you centroids that, unlike the examples, are not integers, and they did see it twice. Let's see what they do this time. Whenever they're mean. Whenever they're mean. Number 17. On number 17, we got an S. Oh, see, why do they do that? S is at 5, 5. Why do they always put S's in, numbers that look like the things together? I don't like that. T is at 11, -3, and U is at -1, 1. U is at, not I. All right, 5, 5 is S. T is 11, -3, a little bit off. I think we can deal. And U is at -1, 1. I kind of like the bigger triangles when it comes to being able to explore more of the space. If it's too condensed, it's hard to kind of draw things. I kind of messed up in one way, though. I made these black. I want to make these blue, or at least a different color. All right. Let's go. I'm going to go from S to U, from U to T, and from T to S. Okay, it looks like my hope is, actually, well, any of these, well, depends on how I want to go with it. Looks like any of these would suffice as decent medians. I'm actually curious to do this. I'm actually curious to draw all 3 midpoints this time, because I think they intersect, all 3 medians, because they connect at different midpoints that are normal. This goes up 4 over 6, so up 2 over 3 instead would be this midpoint there at integers. That's the only diagonal one, though. That one's unfortunate in that way. Let's call this let's call it V and W. I don't want to do X or Y. I'm going to call it Z. This is down 1. From 1 to -3 is down 4. From -1 to 11 is over 12. So half of that over 2, 6. There's going to be that one. Let's call that W. And this one goes from 5 to -3, and half of that's at 1. And it looks like it's going to be right there. So, okay. I'm just getting some midpoints of these ones. We'll call that guy Z. Let's draw those medians. Let's see what those all look like and do. Give me 1 second. Okay. So let's go from here. Now, wherever these intersect should be the centroid as well, which means I wouldn't have to calculate it if it looks like they all are concurrent at an integer set. And I believe they are here. Let's just get them kind of more accurately placed. Okay, so this time I used a different kind of way of going about that for that centroid P. I have no reason to suspect that it would be anything different from those. If you can take 2/3 of any of these lengths, it should be good. It should, well, here's the thing. It should be at a height of 1 because UZ is on that median, right? That's why it's always good to do this one. And it should be, well, yes, it should be there. And this one's a vertical line here. So it should be on the X of 5 and on the Y of 1. So P is at 5, 1. I didn't do the 2/3 thing this time. I just found where they intersected with all the midpoints, but that seems to apply. I didn't dare doing 2/3 of this length. All right, number 18. So that one was a nice problem in comparison, right? Number 18. X is at 1, 4. See, I was going to avoid using X and Y because of the XY axis. And Z is at 2, 3. All right. Let's see what we have here. What we're dealing with. Let's lock it in place. All right. X is at 1, 4. Y is at 7, 2. Z is at 2, 3. Wow. Whoa. Okay. Hold on. X, Y, Z. You know, I was just mentioning how much I like the bigger triangles. I'm going to have to skinny up this thing, the sides a little bit more. I hope that's okay. Otherwise, the thickness would make it really hard to see the space between parts. This one's going to take a little bit more. And I'm not going to bother with the, let's find where the medians intersect. I'd rather do 2/3 of something, because finding where they intersect is going to be, unless it's right there, unless it's at 3, 3, there's no other integer for which they intersect. And it might be at 3, 3. Actually, it might be. Here, take a look at this. I thought this was going to be difficult, but no. Look at the midpoint from X to Y. We go over 1, 2, 3, 4, 5, 6, and down 1, 2. So instead, let's go over 3, down 1 right there. Boom. That's an integer right there. Let's call that point A. And that point A is at 4, 3. 4, 3. Now the distance, oh, okay. I guess it's still going to be at a fraction. So here is a median from Z to A. Now that length is 2. That length is 2. We got to take 2/3 of 2 and do that length from Z. 2/3 of AZ is 2/3 of 2, which is 4/3, which is also 1 1/3, equals 1 1/3. Okay, we're going to go 1 1/3 away from Z to get there. So 1 1/3 like that. And so P is right inside there. I know it's going to be hard to kind of deal with because it's just so small right there. But that should be P. Should be 2/3 away from Z. So that length of ZP, oh, that is ZP. Okay. Centroid. P. That is 1 1/3 away from 2, which is at 3 1/3. So it's at 3 1/3, comma, and it's equal height there, which is 3. So 3 1/3, comma, 3, or 10/3, comma, 3. Either or. Either way. Either way. Either way is fine. All right. I'm good there. All right. Numbers 19 to 22. Tell whether the orthocenter is inside, on, or outside the triangle. Then, I thought that's all we had to do. Then find the coordinates of the orthocenter. I was hoping if that's all we had to do, we just had to make a drawing to determine whether the triangle was acute, right, or obtuse, and that could answer that. So, I mean, as far as answering these were all acute. No, that one was obtuse. Wait a second. Oh, orthocenter. Okay, because this is a centroid. Got it. Okay, maybe it's worth doing these on graphs. All right, L is at 0, 5. M is at 3, 1, and N is at 8, 1. I paused for a second, and I was making sure we had to find centroids of numbers 15 to 18. If it wasn't, and if it was orthocenters, I would have went, oh crap, I got to edit that out and redo them. But I'm good. We're good. We're all good. All right, here's L. Here's M. And here's N. N. Okay. First things first. Now, you could do this in one of two ways. Since you have to find the orthocenter, you could find it first and then answer whether it's on the inside or outside. But it's good to predict it and furthermore understand where you're supposed to draw these to make sense of it. So you should answer whether it's inside or outside first, I guess. How do we answer that? Well, this triangle is obtuse. And because this triangle is obtuse, the orthocenter will be on the outside. They don't tell us to explain why. So I'm just going to write outside. Do it in a different color. Let's use green. Orthocenter's on the outside, so that's part of my answer. Now let's find the orthocenter. Okay, as far as finding, I mean, these should be pretty fast. It's not really much to calculate. You just got to make sure that you know how to draw certain things. The altitudes are going to be perpendicular to any of your sides. Now, the first one I'm actually going to find here is from M to Ln, the altitude. Remember, it's not necessarily a perpendicular bisector unless this is an isosceles triangle. Maybe it is, maybe it isn't. I don't know, I don't care. What I do need, though, is the slope of segment Ln. So the slope of Ln is, you're going down 1, 2, 3, 4, and over 8. So negative 4 over 8 is negative 1/2. Its opposite reciprocal slope is positive 2. Now this is important because from M, I'm going to go up 2 over 1 like that. Up 2 over 1, up 2 over 1. Next time I'll actually plot it as points, so I apologize for doing that. Because, and remember, it's going to intersect outside of the triangle. Which direction? Nobody knows. I do, but I'm going to extend it like this and make sure I get this right. So we're going up 2 over 1 or down 2 left 1 to continue drawing this path. This is the altitude of, drawn from M to Ln. Now the other two, what else do I need? The other two, I need an altitude from N to Lm and from L to Mn. Now the problems with these ones are these are drawn by extension of the sides. This is why the obtuse triangles intersect outside, have an orthocenter that intersects outside of the triangle. This dotted line here, this is not a perpendicular not an altitude, but it is the extension of this side here. I want to extend it out to here because I need to draw an altitude from L to Mn. It needs to be perpendicular, which means it's this straight line at x equals 0 here. I'm going to draw this one like that, straight down. And then, boom, that ends up being an altitude from L, not to Mn, but it is the altitude there from L. Like, that's the height of this triangle if you considered Mn to be your base. Now, I don't need to draw the third one. Remember, they are concurrent, so any two will do. Where did these two intersect? Very perfectly at that orthocenter. I don't know if they call it a point P or a point O or whatever, but I'll call it P. So there's my orthocenter P, and P is at the point 0, negative 5. So maybe I did more over-explaining, so it took a little bit longer. I'll do a little bit better with the slope portion when it comes to actually plotting them, but I might have to do that every so often. You can see the orthocenter is on the outside of this triangle. And remember, the orthocenter has no official mathematical business other than being called what it's called. I guess it's just another fine relationship to say that, hey, triangles have more concurrency than you'd think. It can tell you what kind of triangle it is if an orthocenter is on the outside. I know it's an obtuse triangle, so you can expect some acute triangles, some right triangles here as well. We'll see what else comes up. But they started kind of had it, then easier. All right, y is at 5, 2, and z is at negative 3, 6. Okay, let's do number 20. X, negative 3, 2. Y, 5, 2. Good, we have a horizontal set. Z, negative 3, 6. Even best. I can answer this so fast. I really don't have to do much. I might for your sake. For the sake of the problem. Nah. Oh, those lines have tick. Let's thin those out a little bit. And then Z. From Y to Z. Okay, so we got X, Y, Z. All right. This is a right triangle. It's not just based off looks. It's based off knowledge of horizontal lines and vertical lines being perpendicular to each other. In a right triangle, the orthocenter is on the triangle. That's what I'm answering right there. How on, do you say? Well, if you did want to consider altitudes that we'd be drawing, and remember, I'd only really need to draw 2 of them to find where they intersect. I would draw the altitude from Z to XY, which altitude means the thing that makes it perpendicular from there to there, which is like that. You can't really see it, unfortunately. I kind of made it dotted right there, you can tell. And from Y to XZ, it's this altitude right here. That's where that's drawn. So the orthocenter is on x. X is p, that is negative 3 comma 2. I didn't draw the third one, the opposite reciprocal slope of this from p to there, but that's also because it doesn't really do anything. I mean, if I draw it, great. It's just another way of showing that this altitude intersects there. It is the third one, but that's where it began as well. So that's it. All right, number 21. So there's your right triangle. I don't imagine we're going to get 2 right triangles, but we'll see. Number 21. Because I need to make them harder every so often. Not that I crave difficulty, but I crave nuance. I crave practice with application. Let's go for it. That's a positive one, not a negative one. What I like about this one, at least for 2 of the points, is they are on an axis. I know there's another horizontal line coming. Always good to rely on something where I don't have to have trouble with all the altitudes. All right, A is at negative 4, 0. B is at 1, 0. And C is at negative 1, 3. Now, there's a question within, a very good one, which is, what kind of triangle is this? This is one where you might need to answer it after you do the drawing. But I don't know, maybe I can look at this drawing and tell, because I can't tell if that's a right triangle or not. I'm going to guess it's not. I'm going to guess it's probably acute. The reason is because I'm not the reason, but I don't believe this is 1, 2, 3, 4, 5. I don't believe it's a Pythagorean triple, so I don't think it's a right triangle. My guess is going to be acute, but we'll find out. We'll find out, right? I'm going to start by drawing the altitude here from C through AB, and I might as well just draw it large because it can intersect anywhere on that altitude, right? Who knows where specifically, but there's an altitude, not a perpendicular bisector, an altitude from vertex through there. Let's do a second one. Let's go from A to here. Now, from A to CB, again, I don't know if it's extended or not, but let's find the slope of CB. The slope of segment CB is down 1, 2, 3 over 2, down 3 halves. So its opposite reciprocal slope is 2/3. So for A, from A, I can go up 2 over 3. Oh, look, it lands just right there. Perfect. And that's going to be the orthocenter. Up 2 over 3, like that. We'd continue that path. And I'll just keep continuing just to drop more and more. It's like we didn't know for sure until we knew whether it was acute or obtuse and all that. But from here, we can then draw, boom, that guy. I guess close enough when it comes to drawing. So that is, yet again, another altitude. That goes right here. It's just showing it. And then, boom, there's that point of intersection. It looks very integer-like. There's my orthocenter P. P is at negative 1, 2. Negative 1, 2. The third one does not need to be drawn. This was an acute triangle. Therefore, this was inside the triangle. I mean, I'll say it the other way. This was inside the triangle. Therefore, this triangle was acute. It looked acute. Just couldn't quite tell. And number 22, I see construction below. I'm probably going to have to use the compass. Number 22, I got T at negative 2, 1, U at 2, 1, and V at 0, 4. This seems isosceles. I believe it is. That doesn't mean whether it's acute or obtuse or whatever. Just it looks like it's going to be an isosceles triangle, which might be helpful for finding points more easily. I don't know. We'll see. T is at negative 2, 1. U is at 2, 1, and V is at 0, 4. Definitely isosceles, if not equilateral. I don't think it's equilateral, but definitely isosceles, perhaps acute. Let's get my color scheme going. All right. Okay, orthocenter. Well, this is definitely acute, so it's going to be inside the triangle. And, well, we can draw one of the altitudes from V to TU. Excuse me, I'll start with that. It's basically the y-axis. So somewhere on the y-axis we go at 0, what? We'll figure that out. Let's find the slope of one of these guys. Doesn't seem like it's going to help too much to know this, the other information. But the slope of, let's say, segment UV, that's going to be down 1, 2, 3 over 2, just like before, negative 3/2. So the opposite reciprocal of slope of that is going to be 2/3. So from T, I can go up 1, 2 over 1, 2, 3. Oh, don't speak too soon as far as ease goes, Mr. Robinson. This looks like it's going to take a little bit more. So if I do this 2/3 thing, you can see that it has a fraction that it's going to cross through, basically the y-intercept. This is an instance where, you know, the lecture portion of this was talking about finding equations of lines and stuff like that. Well, it might be kind of useful here. So where do these guys intersect is the question. What is that point P? Well, point P is the intersection of the line x equals 0 and y equals whatever this equation is, or y equals whatever this equation is, you know, in terms of mx plus b, it's the y-intercept. So really, I just need to find the equation of this line. By the way, this is an altitude, that's an altitude. So let's just find the equation of the line that goes through T. Remember, T is at negative 2, 1. That is an xy. That is an xy. So I do have an equation here that is y minus y1 equals m times x minus x1, like that. Now that doesn't answer the question, but whatever the y-intercept of this is will answer that question. Let's go ahead and distribute 2/3 into here, and then I'll add 1 to both sides of the equation. So I'm using point slope form, not the way you have to do it. I'm using point slope form. Y minus 1 equals 2/3 x plus 4/3. Add 1 to both sides, I get y equals 2/3 x plus, now 1 is also 3/3, so 4/3 plus 3/3 is 7/3. This is your y-intercept, and that should be P 0, 7/3, because it's on, you know, it's the y-intercept, it's where it crosses and intersects with the other guy. That should be your orthocenter. So my P will be at 0, 7/3 or 0, 2 1/3. Either or works with that. And that's just the way that I mathematically went about that. I hope it kind of makes sense what I did. Remember, I used point slope form. Something that we did in a previous section, like at a previous time, was we used y equals mx plus b and plugged in an xy that was a known point, such as negative 2, 1, to find the b, which is the same thing as here. Totally works out. All right, I'm going to finish with that one there. That's number 22. Let's move forward. Numbers 23 to 26. Draw the indicated triangle and find its centroid and orthocenter. Okay, and there's a lot that's kind of expected of us. We also have to draw an isosceles right triangle. I wonder if they expect me to use a compass to construct that portion as well, or if I'm kind of just good to do what I do. I suppose I will. So here's how we'll go about this. I'm going to draw, and I guess I'll draw them kind of large-esque, but I'm going to draw a segment. Let's kind of thin this out, though. I think the thinner is going to work out. I'm going to draw a segment right here. Should I do it just with... Okay, I'm going to draw kind of a larger segment, and I'm going to kind of end up cutting it a little bit, because I need to draw something perpendicular, right? We don't know about perpendicularity yet until we do it. So let's use, where's my compass tool? I'm going to use this right here. Okay, from the... Give me a second. I'm going to draw a point right here, and then some point, like, I want to make it kind of close to the end. Wait. I'm going to cut off this side a little bit. I'm going to draw points right here. Okay. From these 2 points, boom and boom, I'm going to find a perpendicular bisector. So let's spread that. Sorry. Let's make it go upward. I don't have enough room because my compass thing. This is the problem with this. This is what makes this take a while. I need to like make it fit. All right, from this point, I'm going to spread this out a little bit. Let's change its color. Let's draw one arc and a second arc. Now with these 2 arcs, what I'm going to have are, no, don't change this size. What I'm going to have are these 2, where the 2 arcs intersect, and I'm going to draw another line through that guy. You would basically use a ruler to do that, right? Let's thin that out a little more, sorry. Let's thin it and extend it. Okay, we've drawn perpendicular portions. They said an isosceles right triangle. We have the right part of the triangle here, all right? What I'm going to do next, these other points are now irrelevant. I just used them to, well, I didn't need points necessarily, but I used something to draw something perpendicular. Now all I need is 2 points of equal length. This is where I can just size this out to whatever I want, because they didn't give me a specific length. And I can just draw an arc here, and I can draw an arc down here. These should be equal length now, and I'm going to connect those guys together right here, like that. There. That should be my isosceles right triangle, where the legs are congruent. The hypotenuse is obviously longer. And there you have it. There's the isosceles right triangle. Okay? So from here, if you don't mind, I'm going to now shrink things to match up with those points. I'm going to erase all my arc marks and all of a perfect one like that. You would probably do the same kind of erasing to make that thing the way that it is. So here we go. And that should, whoops, and that should be pretty to scale, assuming that my compass thing did as it was supposed to. There we go. So there's that guy. Let's get rid of all those. That's my compass construction. That did nothing more for me other than make my triangle. That's why I said these problems might take a while. Okay, cool. There's the beginning. Let's call that, they tell us to call it anything? No, let's just call it ABC though. ABC. ABC. We got to find the centroid and orthocenter. Now, to find the orthocenter is going to be pretty, I'm trying to figure out how to label it. Orthocenter should be pretty fast. The orthocenter is going to be on the triangle. The orthocenter is going to be right there. We know that because it's a right triangle, it will be there. So let's call that orthocenter. Already taken care of. Good to go. They shouldn't expect you to do more from that. The centroid should be from intersecting your medians. Now, I'm going to find 2 medians here. I'm going to find the ones from, and this should also go, I guess, kind of quickly. To find the medians, you saw what we did previous, or you saw maybe what the lecture portion did. You want to draw perpendicular bisectors. And I'm just going to draw a large one right here because I want it to apply to both segments, if you will. That length is what, 104? So let's flip it on this side, make it 104. Okay, so with that, and now from A, I'm going to draw another arc and find where those two intersect. Okay, boom. And then also with C, on B, I'm going to find where those 2 points intersect. Oh, I didn't make my arc big enough the first time. Timeout. 104 from C. Wow, clearly I'm not going to make this path the exact same both times. Close enough. All right. From B, I'm also going to draw where arcs intersect here. Okay. So remember, the next thing that I draw here, these are technically perpendicular bisectors, but the point isn't to make perpendicular bisectors. The point is to find where the perpendicular bisector intersects with each segment. So this guy intersects here at that point. This guy intersects here, closely as I can make it, intersects here at that point. Those are the midpoints of each segment for which we can draw medians. Everything else I can erase. Now what we want to do is draw a segment from B to that point, here, from B to here, and from A to this other midpoint here. These are 2 of your medians. We have constructed effectively, these are all congruent. These 2 are congruent to each other. These 2 are congruent to each other. But because it's isosceles right triangle, those would both be congruent in their own right. So this right here would be the centroid. Which does mean that this length is 2/3 of the entire thing. This length is 2/3 of the entire thing. Things like that. There's number 23. Let me pause this for a second for myself. Okay, sorry. I had a job that finished rendering for something, so I could start uploading it to YouTube now. So this one doesn't get in the way when I start uploading this one later. I want to just pause it and get that taken care of. All right, that was number 23. Let's jump to number 24. We need an obtuse scalene triangle. This one's probably easier to construct because there are no real rules other than making sure that they are different lengths. For you, ideally, and making sure that it's obtuse. For you, ideally, you can kind of just draw 3 lines and just kind of, in your own eye, make sure that they are different lengths, right? So if I draw a length that's like, and also make it obtuse, of course. If I draw it, like this right here, I think there's enough showing that this is both obtuse and scalene, that this is clearly the shortest side and the next longer side and then the longest side. So just, using a straight edge and doing that, great. I didn't need to use the compass for that part. So that's a good beginning for myself. Now, regarding this, I also have to be careful with respect to size because I need to make sure that the orthocenter can be seen here because the orthocenter will be outside of the triangle. I will begin this time, however, with the centroid. And I just need to find 2 medians the same way that I did before. I'm curious as to whether finding orthocenters at the same time is practical. I have to think about that. No. Okay. So, meaning using the same arcs. The answer to that is no. So, first thing I'm going to do is find 2 perpendicular bisectors, kind of like I did before. So, arcity arc. And on the other side of this, where B is, I'm basically finding the midpoint of BC right now. Arcity arc, like that. Let's go ahead and draw through that guy right there. And then we'll have one of our 2 midpoints that are going to be needed. So here's one. Boom. Okay, let's do a second one. Let's delete all that stuff. Okay, let's do a second one. Let's do this big guy here. Stretch it out a little bit. Hope that's going to be big enough. And then over here, whoa, 214, 214. Okay. Sorry, my own compass tool is not, it's just so much easier to do on paper. Another perpendicular bisector, all that's needed is just the bisector portion of it though. Just where does it intersect? It's going to be very important. Okay, so that will be right here. Okay. Great. Okay, so what we'll now have are 2, well, let's draw 2 medians. Draw one from B to here, like that. And let's make it look a little bit better. And then let's go from A to this other midpoint here. All right. And I didn't do the one with C. It's aight. We have found the centroid right here, drawing 2 medians because these are congruent and these are congruent, right? So therefore, centroid. I should call something metroid. All right, orthocenter. You need 2 of these as well. Yes, my screen has me having drawn one that was completely horizontal, but we don't know that, if that makes sense. We're not privy to that knowledge. Here's how you would do altitudes. I guess I do want to start deleting some things so I can give myself more room. So here's how you do altitudes. We're going to do perpendicular bisectors again in their own right, however. One of them that I'll do is hold on, I'm trying to think where these intersect. They intersect outside of here. So look, here's going to be one of the altitudes. I have to make it myself later, but one of the altitudes is going to be like this guy right here, right? This thing is the right angle drawn because it's vertical to this horizontal, right? My computer tool let me do that. It's the vertical to this horizontal, which means I need to extend this side. But that's what I'm first going to do. I'm going to look to extend that side, BC, and figure out how do you get that altitude through compass construction. And here's the answer. You got to find the perpendicular bisector from B to a new point over here. So you need to basically make a little, not an isosceles triangle, but you need to find the point that A is equidistant from with B and with over here. So here's what I'm going to do. I'm going to find the length from A to B, This thing. Hold on. I need to find the length from A to B. I'm sorry if my words are jumbled when I want to explain that, but I want to find the length from A to B and draw that here. See, this isn't going to be perfect, unfortunately. Let's make it. Let's force it to be a little bit longer. So see this length right here? Boom. Then on the other side, boom, right there. What is that other point? See this guy. This guy right here. Because if you remember your perpendicular bisector theorem, the perpendicular A should be on the perpendicular bisector of a segment that A is also equidistant from its endpoints with. So if A is equidistant from this point B and P, which it is, that's what the curve is showing, then A is also on its perpendicular bisector if there was a made-up segment. So to draw its perpendicular bisector, now we got to basically make arcs that intersect. Well, A is on it, but you still got to draw the bisector itself and just draw a segment through A. So all I got to do really is just extend. This is fine. I just got to extend something downward like this. Make where these two arcs intersect, where P and B intersect. Boom. And now I just got to draw something from A down to there. And then, therefore, it should be its perpendicular bisector. That would be one of them. So it takes a little bit. Takes a little bit to do. So there's one of them. Look, kind of in essence, it's a perfect drawing through that. Therefore, this is an altitude. And I do want to draw it kind of longer because the orthocenter will be outside of the triangle. Somewhere outside of here it will be, and I did want to extend it like that. That totally works. I don't know what things I want to get. Like, I feel like I'm proud of my work, Pa. I want to keep all the work that I have. Well, for the sake of what we do, I'll at least extend it like that and fade it. So you can see that it's still kind of there, but not part of the triangle. Okay, there's one of the altitudes. Okay, let's do another altitude. Let's do from B to AC. So same thing, like A is closer. I don't know how to say what I'm saying. A is one of the points on the segment AC, clearly. But A is also the closer point to B than C is, so I can just use A as one of those points. I don't have to, but I want to see something. If something's totally accurate to it, I would prefer to use it. So I guess that's the idea, right? I didn't have to use B itself, but because B was one of the points, it was just nicer to use. So if I use these two right here, I can just stay on that point right there and just draw myself altitudes. I know it's going to go through this orthocenter part right there, but that's okay. So there's a point, and there's just some unknown point right there. You don't have to call it P or anything, but just know where you're drawing your arcs through. Oh, wow, intersected way up there. Good thing I drew the whole bit. So I'm going to draw now a segment that goes all the way up through there. Boom. And that is an altitude because it's the perpendicular bisector of those two quote-unquote endpoints. This endpoint was a made-up one. A was not a made-up one right there. So B, oh, I have to keep extending this. So B, altitude, boom, goes like that. Okay, so that would be an altitude right there. And then this ends up being the orthocenter. I didn't draw C's thing, which would have been an extension of this line and the altitude that goes through, boom, whatever, but that's where that one would have intersected as well. So once I kind of erase everything, I have the centroid and the orthocenter, as you see right there. I lost my B letter. B. And again, orthocenter, see, I wish the orthocenter had more mathematical merit with respect to what it does in the triangle or outside the triangle, if you will. It doesn't really. It's just that's where it is. That's where all the perpendicular things would intersect. But I'm going to leave it like that. Now, you'd have to draw yours like I draw mine for that to work out best, but whatever. All right, number 25, a right scalene triangle. I'm wondering if there's not a faster way. Well, I'll tell you what, it's going to be the same as number 23 when it comes to the orthocenter, but I wonder if there's a faster way to use, because you get to draw a first segment, but when you draw this altitude, can I use it? Well, no. Sorry, I'm talking to myself. It's okay if you don't have to understand what I'm saying in my head. I was wondering if there was a way to use one thing as a median. Well, I could use that as a median if I draw the perpendicular bisector. That's just draw the altitude. No, okay. Okay, I'm good. All right, I'm going to do another right angle thing like I did before. Let's take one of these guys like this point right here. Let's just make another new point up. Like this guy right there. Let's find its perpendicular bisector. So let's do one like that. Let's do one like that. Okay. Now, of course, mine will be a vertical line, but I'm showing you how you can draw your own. I'm going to make it go downward, though, this time. All right. There's concept. Now let's erase parts, right? Shrink it, erase parts right there, and there's my right angle. The orthocenter will be on the right angle itself. To make it scalene, just make sure the legs are separate lengths. And I'm probably not doing a lot of that right now. So let's see, let's shrink this guy up. Okay, those are clearly separate lengths. Hypotenuse will, of course, be the larger length. So use a straight edge and just connect those right there, and you should be good to go. There's a scalene right triangle, where once again, the orthocenter will be, they're doing us a favor there by not having to do more, but the orthocenter will be, for this one, on the right angle itself. Ortho center. And let's do two medians, shall we? So let's do median here by drawing perpendicular bisector of these two. Boom. Let's find out where those two guys intersect and make that a midpoint of that segment. I didn't call this ABC. You know what? It's not required to call it ABC. I just wanted to say out loud what I was doing. But here's a midpoint, which makes these two guys congruent. Whatever. So therefore, excuse me, did I call that a median or a midpoint? That's a midpoint for which I can draw a median. The median would, I'll draw the median later. And then let's do one for the, let's do it for the longer side here. I forget if I did that last time or not, but this time I will. Sorry, this tool is really hard to work with. I just don't have much room on it. At least when it comes to capturing video for you guys at the same time. I'm sure I could make this a lot more easily handled if I wanted to. Okay. Yeah, it's a perpendicular bisector, but it's also a midpoint. Close to one. Okay. Midpoint. Okay. Which means these two are congruent. Okay. I don't know why I never did a single tick mark thingy. That's all right. I don't want you to confuse them for random accidental marks, which they're not. All right, we're going to do a median from this guy, an unknown named vertex, to this unknown named midpoint, and from the right angle to this unknown named midpoint right there. And boom, hey, we have a centroid. We have a centroid. It is right here. You got 2/3 lengths. Centroid. Right there. I was trying to draw an arrow. All right, there it is. Okay, let's erase all that and keep going. I got one more to do. I'm assuming it's going to be acute, maybe even isosceles. We'll see. All right, there's number 25. Let's go to number 26. Yep, acute isosceles. Number 26, acute isosceles triangle. Okay, this might even be faster to construct. So check this out. If I construct a single point, now this time I'll label it, call it A. I'm just going to draw an arc. Watch this will be fun. I'm just going to draw an arc from A, just around. Make it kind of big. Whoop. Any 2 points that are on this will make, first of all, any 3 points make a triangle, but any 2 points on this will be equidistant from point A. Like this point right here, if I called it B, and this point right here if I called it C. These are both equidistant from there. Therefore, when I connect all these, I'll make an isosceles triangle. It was really cool. You just got to make sure that it's acute. And I guess this looks acute. We'll be able to tell when we connect them all. So that makes an isosceles triangle right there. And this time I'm making nothing vertical, which probably hurts more than helps. But when it comes to compass construction stuff, this way I can't really rely on just saying, oh, I could just use my tool to do this. So that's very isosceles. Excuse me, not isosceles. What is isosceles? It's very acute looking. So these are both congruent here. Fantastic. Okay, with those being congruent, I'm trying to remind myself if there's anything that would help me by knowledge of congruence with this. You know what would help is drawing the perpendicular bisector from A to BC. The reason that would help is because it would serve as both an altitude and a median at the same time. So that would take care of one for both of these things. In fact, that arc I drew before is not relevant. So if I now just draw a single arc from C, I need to make it long enough. I need to make an arc from C and an arc from B. I need to make them long enough so that when I connect their point of intersection here, will be something I draw from A through here. Okay, so I go from A and through. I know you probably can't see them both together. Now you can, because this is a very tight range here. Okay, so this right here serves as a perpendicular bisector. It's both the altitude and the median at the same time. So those move. Those are congruent to each other, and it's a right angle. And I extended it very far. I won't actually need that whole distance. This orthocenter will be inside the triangle, but I do need to make sure that that stays. You know what? I need to make sure that that stays on point. So I'll just keep it long. So we'll keep that there. I don't need the arcs anymore, but I will keep that like that. So that's a good one to have for both. That's where that benefited. I need to draw a second altitude that intersects with this, and I need to draw a second median that intersects with this. I'm going to kind of put these down lower like that. Let's see. To do the altitude, I'll need another perpendicular bisector. To the median, I need a perpendicular. Let's see. I have two different perpendicular bisectors to do. So I'm going to go on AC right here, and I'm going to show you the difference between. This triangle is nearly equilateral. I don't think it's exactly. I think these two lengths are longer than this one, but the median and the altitude, I was going to show how they're different, and they'll only be slightly different. So I hope that that's okay. Let's start with the median. I'm actually going to change color to purple here. Start with the median. I'm going to draw perpendicular bisectors from points for segment AC. So here and here. Remember, I don't need the altitude portion itself. I just need where these intersect. So these will intersect right I hate when it snaps like that. If this would save a lot of time if it didn't. So these intersect right here. Okay. Therefore, I can draw a median from B to there. And when I draw that, I'm not going to label it. When I draw, actually, yeah, I will. I'll call this one M for median or for midpoint. When I draw that from here to here, and I'll erase all the other stuff, I'm sorry. When I draw that, I've now found the concurrent point between these two, which makes my centroid. Centroid is there. This is not necessarily perpendicular to that segment. You saw how close they were to being the same, actually. They were very close, but not quite the same. So not perpendicular. Okay. Now we're going to draw the perpendicular one. We're just going to go a little more right there. It's going to be very close, and I apologize for them being so close. Maybe I shouldn't have made it so equilateral. I didn't intend to, I'll be honest. The B and C were just made up points. But let's see what we got. But this is, by the way, this is the centroid. Yeah, gee, I should have made them a little... Don't make it equal... Well, if you make it equilateral, then the centroid and the orthocenter will be the same. So maybe you do want to make it equilateral. I don't know. It depends on what you want to do with it. Okay, I'm going to use this point C as one of my points because I guess theoretically this will be closer here than the other side. So let's change this to green now. Let's just make another arc there. Sure. And let's now use this arc as a point. C is the other point right there, and let's make the perpendicular bisector of those two. That'll be the altitude. Wait a second. What am I saying? I drew the wrong arc. I drew the wrong arc. Let's draw an arc from B through C. I was doing the wrong thing. I was thinking of something else completely. Let's widen out B to C's length, like so. Sort of. And then, boom. Yeah, see, it's going to be a little bit shorter there. Boom. So this point right here is the other end point I got to do a perpendicular bisector with. So it gives me the altitude from B to there. So let's do that. Let's shrink that up. This is nearly equilateral, guys. Apologies, apologies, apologies. I should think this stuff through beforehand. All right. Where does this guy intersect with this guy? This one won't be perfect because you can see how it extends beyond C a little bit, but that's just because of the way that this compass thing snaps. I can't do anything about that. But I can make it as close as I so wish. So B, from B through to there, boom, nearly the same, but not quite exactly the same. Because it's nearly equilateral, but not quite. Okay. And that, my friends, is an altitude, which makes this, my friends, the orthocenter. Okay. Wow, very close to each other, which meant this was very close to being equilateral. I'm sure. Now, listen, they haven't asked it yet. They haven't asked it yet, but, and I haven't looked beyond it. We still have 25 questions to go or something. So we're halfway through. I'm almost certain they'll ask something about equilateral triangles. How do you know the center? Or if the centroid and the orthocenter, I'm going to predict this. If the centroid and orthocenter are the same point, what kind of triangle is it? Explain. Guarantee that's a question. I can't actually guarantee it, but we'll see. All right, that was number 26. Let's move on and hope it's not construction. Number 27 and 28, error analysis. In exercise 27-28, describe and correct the error in finding the length of DE. Point D is the centroid of triangle ABC. To remind you, in a centroid, that's the medians that are drawn, and these lengths are 2/3 of, from the vertex to the point, or 2/3 of the entire thing. So they say DE is 2/3 the length of AE. It's not true. So that's kind of the beginning part. The calculation is correct afterward, but DE is not 2/3 the length of AE. DE is 1/3 the length of AE. DE is, I'll actually say what is 2/3. Not 2/3 the length of AE. AD is 2/3 the length of DE. So you can either find the 2/3 length and use the 12, or and then subtract it, from 18, or say DE is half of AE or 1/3 of, half of AD or 1/3 of AE. So DE is 1/3. They never expressed that out loud, but they probably should have. DE is 1/3 the length. So that's what we'll use. 1/3 of 18 is 6. So correcting that. We get 6. Okay. And yeah, so just having the knowledge that the 2/3 is from the vertex to the centroid, not from the side midpoint thing to the centroid. Okay, the length of AD is 24. That's just this guy right here. That's not the entire length. They say DE is 2/3 of AE. Also not true. It should be half of that, right? So, in this case, DE is not 2/3 of AD. It's not even 2/3 of AE. It's half. of AD. So, because 1/3 is half of 2/3. So, DE, the little guy, is 1/2 that of AD. AD is 24. So, it is 12. AE would therefore be 36. Okay, we got to write proofs. Numbers 29 and 30. Didn't know if we were gonna. Didn't know that we were gonna get those. All right, number 29. Write a proof that the angle bisector from the vertex angle to the base of an isosceles triangle is also a median. Okay, so I'd like to probably use the givens that they used before. I'm going to make a drawing. I don't know how they said everything in full as far as the givens are. Like, this is isosceles, stuff like that. But I'll probably just make up my own. Okay, so we'll call this ABC. We're given an angle bisector and we're given an isosceles triangle. Okay, those two things are noted. So we're going to make that. And the angle bisector is from the vertex angle, the one that's like, yeah. Let me just draw it. From B to this point, I'm going to call it D. Okay. And we might have to do that for number 24 as well. An isosceles triangle also for that one. Okay. So, what do we say? Angle bisector. So this guy there. All right. I'm just going to go straight to the 2-column part instead of writing given and prove. I just hope I have enough room to do it with this diagram, but I really want to use the diagram with this as well. So statements and reasons. See, this is the part, I don't know if I'll have room, but I want to use the diagram with it. Like, I want you to see the diagram as I go along with it. Whoa. Pretty big. Okay. I probably need more room on the reasons end. Okay. Number 1. Triangle ABC is isosceles. That's given. Maybe if I have enough room to write these givens, the shorter ones here, then I'll have enough room on the bottom. Number 2, segment BD bisects angle ABC, also given. Okay, y'all. From statement 1, we can state that these two segments are congruent. We can say segment AB is congruent to segment CB. Right? Those two are congruent. That's the definition of an isosceles triangle. Now, this is one of those things where some people would write this statement right after that statement, despite the fact they're two different givens, and I probably should have. But I'm telling you which ones go into which one here, so hopefully you get that. Statement 4. Let's go based off of this guy. BD bisects the angle. These two angles are congruent. That's the definition of angle bisector. So angle ABD is congruent to angle CBD. Oh, I need another thing here. Okay, now I think I don't have room the rest of the way. So that's definition of angle bisector. Okay. Now, I already labeled those parts. Generally, they would just state given. They wouldn't mark it for you. You would mark that with the statements, and then you creating those markings would have those down. So now we have them written. All right. Now we got to create for ourselves, procreate. Our goal of these always is, guys, to create kind of congruent triangles. I want to make congruent triangles out of this. So my thing here is making segment BD congruent to itself. BD is congruent to itself by the reflexive property. It's a shared side in both triangles here. Reflexive property of congruence. I'm just going to write reflexive prop. And now I have a side angle side case. Side angle side to state that these two triangles are congruent to each other. Triangle ABD is congruent to triangle CBD. Now, I'll let you know, guys, full disclosure, number 30 looks like it's the same kind of thing. Altitude, no, it's not the exact same thing. But I'm going to copy and paste a lot of this, and I'll just state it out loud. This is the side angle side congruence theorem. Okay, triangles are congruent. Corresponding parts will therefore be congruent. We need to show that it's a median. To show that it's a median, we need to show that these two guys are congruent to each other. And now we know that because we know the triangles are congruent. So segment AD is congruent to segment CD by CPCTC. Segment AD is congruent to segment CD by CPCTC. Corresponding parts of congruent triangles are congruent. According to their proof, it didn't look like that we had to do this whole D is the midpoint of, by definition of midpoint, and medians go through midpoints. It looks like their median, in fact, their median definition, let me go away from this for a second and find their median definition and say how they said it. They say it goes through the median, it says midpoint. Median is a segment from a vertex to the midpoint of the opposite side. They didn't say it, but I feel like I gotta say it. You know, I gotta be complete with that, so I'm going to. So let's go back. I'm sorry, I was just reading their definition. So let's go a little bit more. Let's say that D is the midpoint. D is the midpoint of segment AC by definition of midpoint. And then therefore the AD is the median. See, or BD is the median. See, I don't know if that's a required statement. I'm going to say definition of median after that, because that's what it is. BD is the median. Is a median of triangle. Is that what we say? Is also a median. It's not the median of the segment, right? Or wait, is it? I don't know if medians do things in segments of triangle ABC. Why did I erase the to write the? BD is a median of triangle ABC by definition of median. The median's definition is a segment that goes from a vertex to a midpoint. We proved that D was a midpoint because of the congruency part. Okay, there's my proof there. So 8 maybe could have been skipped. I believe they skipped it in one of the lecture portions, but I wanted to go full on definition there. I think next time I would skip that, actually. Now that I think about it, if they told me something was a median, I think I would go straight to the congruent parts by saying definition of median. I don't think I'd say median to midpoint and midpoint to congruency. So, okay, there's that. All right, number 30. Let's use similar concepts. I can probably copy and paste. Not all of this, not at all. They're giving us a different construct completely, but I wonder how much I can really bring over. So allow me to copy paste first. I'll delete the stuff that's not needed, necessary, what have you. I definitely got to get rid of that 29. But I want to use the same drawing and a lot of the same bits, like reflexive property, all that. They did say isosceles triangle, so I'll use that. This time we talk about altitude, though. So instead of here, we're going to say that it's isosceles. This is no longer the given there. Yeah, you know what? We probably got to get rid of a lot of this. But at least I have stuff pre-drawn this time that I don't have to... Yeah, let's just kind of get rid of that bottom part. That, you know what? That was faster. All right. So ABC is isosceles. That's given. The next part is that we know that there's an altitude here. So BD, segment BD, and remember, that might not be drawn. It would just, we just say it. Segment BD is an altitude. What are we proving, by the way, this time? Of triangle ABC. Oh, you know what I want to do this time? Sorry if you already started writing. Let's this time put this right next to this. So segment AB is congruent to segment CB by... See, this is what I could have kept over here, but definition of isosceles triangle. This time I'm going to actually put this next to it. All right. BD is an altitude of triangle. ABC is also given. We're going to show this as a perpendicular bisector, by the way. Okay, so altitude, so this is one of those things. Does altitude mean I have to state perpendicular? Does perpendicular mean I have to state right angles and all that kind of stuff. Because this can be a lot of steps if I do all of that. And altitude by definition is perpendicular. So I'm going to go straight to the right angle thing. So sorry if it seems like it is a skip step. Sorry, book. So angle ADB and angle CDB are right angles by definition of altitude. I'll go straight to that. Sorry if a step is skipped. Oh, you know what? I might want to put, I might want to put I'm still going to have this. I might want to put the perpendicular part. Reason being, what am I doing? Reason being is because we have to prove it's a perpendicular bisector. So we might want to state perpendicularity to begin with. So segment BD is perpendicular to segment AC by definition of altitude, and now they are right angles by definition of perpendicularity. Definition of perpendicular lines. There's going to be a lot of definitions here. And then you want to say that these are right triangles. I don't want to state they're congruent. My proof is going to be an HL proof. I'm going to prove hypotenuse and legs are congruent. So now right triangles, by definition, are right triangles. So triangle ADB and triangle CDB are right triangles. I said I needed more room on the reason side. I think I actually need more room on the statement side. By definition of right triangles have right angles. Now that's important for the HL portion. HL can only exist in right triangles, and we show that. Now BD is congruent to itself by by reflexive property. BD congruent to itself by the reflexive property. Those are the legs of each of these triangles. My handwriting gets really bad on these. Now triangle ADB is congruent to triangle CDB. Triangle ADB is congruent to triangle CDB. This is by HL. This is the HL triangle congruence theorem. I have a right triangle, congruent hypotenuses, congruent legs. Now we get to use kind of the same things as we said before. We get to say that we're proving it's a perpendicular bisector is also a perpendicular bisector. So we got to say now these two are congruent. Segment AD and CD are congruent by CPCTC. Segment AD is congruent segment CD by CPCTC. Congruent segments means that the segment bisects this thing. And then I think we'll be done because we got the perpendicular portion there already. So I'm not going to say the midpoint part in between. So BD bisects segment AC by definition of bisector. Maybe you can say it's a perpendicular bisector by definition of perpendicular bisector, but that's, this part already concludes that. So statement 4 and statement 10, I think, are it. Perpendicular bisector. We already see the altitude thing means we already know it's perpendicular. If it didn't know that, then I stated it there. I'm good. I'm not going to write a statement 11 saying it's perpendicular bisector by definition of perpendicular bisector. It's perpendicular to it. It bisects it. Boom. I think that's what they wanted to know. Does it bisect it? And it does. Okay. I talk a lot. Number 31. Oh, 31 to 36. Number 31 to 36. We got an always, sometimes, never. I'm going to type these out. I feel bad sometimes I would force my students to type it out, to write it out on their thing. So let's do that. Otherwise, they just look at a word, always, sometimes, never. It doesn't do enough. The centroid is blank. Centroid is not misspelled. The centroid is blank on the triangle. The centroid is the intersection of the medians of your triangle. The medians are always inside your triangle, no matter what type. The centroid is never on the triangle. They said to explain it. So Whoops, I guess I'll just do it right after. I just said it, though. The centroid is the intersection of the medians, and medians are always inside the triangle. So it's never on, it's also never outside. It's always inside. Good. I like having a never to begin with. They always kind of start with always, and let's go the other way. All right, number 32. The orthocenter is blank outside the triangle. It's sometimes. The orthocenter is sometimes outside the triangle. Remember, whenever you have a sometimes, the best medicine for explaining it is say when it is and say when it isn't. It is outside the triangle. Orthocenter is not misspelled. It's outside the triangle when it is obtuse. It is not outside when it is not obtuse. Clearly stated. I mean, you'd have to be aware of that knowledge. But yeah, there's that. Number 33. A median is blank, the same line segment as a perpendicular bisector, or a median. A median. All right, let's see. A median is blank sometimes. We've seen a very specific example. The same line as a perpendicular bisector. So a median does bisect the side. That part would be always. A median bisects the side, but to be perpendicular to the side, this would have to be the median from the vertex of an isosceles triangle. So to be perpendicular to the side, it would have to be a median from the vertex of an isosceles triangle. That does also mean, by extension, equilateral triangles. From the vertex joined by the legs. I believe that's the one that they call the vertex, therefore. All right, number 34. An altitude is blank the same line segment as an angle bisector. I believe this is also for isosceles triangles. So an altitude, I think a lot of these will be sometimes, is sometimes the same line segment as an angle bisector. Like number 33, this is only true from the vertex of an isosceles triangle. And again, equilateral triangles. Yeah. I can't think of other other times when that is true. I think it's only got to be isosceles triangles. Apologies if I miss thinking about one of the things it can be. The centroid. This is where the question shows up. I guess it was a different kind of way that they said it. Here it is. The centroid and orthocenter. What did I say? The centroid and orthocenter they're sometimes the same point. Not often. Sometimes the same point. There's only one case when this is. This is only the case in an equilateral triangle. Because all of them would have to be perpendicular bisectors that are also angle bisectors, that are also medians, that are also all these kinds of things. This is only the case in an equilateral triangle. So when does it work? Equilateral triangles. When doesn't it work? Not in equilateral triangles. In not equilateral triangles. All right. And number 36. Number 36. The centroid is blank formed by the intersection of three medians. Always. That is its definition. The centroid is always formed by the intersection of the three medians. This is the definition of a centroid. That's how I can explain it. All right, that is numbers 31 to 36. Let's go to number 37 and 38, writing. Compare an altitude of a triangle with a perpendicular bisector of a triangle. All right. 37. So, okay. I might draw something for you, but I'm just going to kind of explain it. So an altitude of a triangle. So listen, both of them, both an altitude and perpendicular bisector are drawn perpendicularly to a side. The difference is the altitude is drawn from the vertex of a triangle, and the perpendicular bisector is drawn from the midpoint of a side of a triangle. So they can be two different things. They often are when they aren't in isosceles triangles. Kind of the same thing we keep bringing up over and over. So in some random scalene triangle, such as this one right here, this would be an altitude right here. Okay. That is the altitude. Normally it's more of a segment, so I would probably just shrink it to that. And then the perpendicular bisector, you know, wherever the midpoint is, let's say that this is the midpoint right here, this would be the perpendicular bisector. Because it would make these things congruent right there. So that guy, I don't know if that's perfect or not. Because now these are congruent to each other like that. That's the perp bisector like that. So that's the difference between the two, because they're both drawn perpendicularly, but there you go. Only the same if it's like isosceles. All right, number 38. Compare a median, an altitude, and an angle bisector of a triangle. Okay. It's hard to compare three things as far as like they're same like this, they're different like this, whatever. But, okay, a median bisects the side opposite the vertex of the triangle it's drawn from. See, it's still drawn from a vertex. So I guess that's one of the things, in that a median is like a angle bisectors, that they're drawn from a vertex or from an angle. Whereas an angle bisector bisects the angle it's drawn from. That because like they don't have to be the same, and I don't think people realize that. So let's say I'll erase this in a second, but let's say I have, and I don't know if you'll be able to tell this or not because I probably can't draw these very well, but an angle bisector may be this guy right here, right? Imagine that this thing is bisecting this angle and it's like, okay, these are congruent, boom, boom. That's an angle bisector. Well, the median needs to bisect the side. So the median might be more so, sorry, I'm trying to change colors and stuff, but it looks like I'm not going to do too much. The median is more bisecting the side, right? So this is the part that says these two are congruent like that. Now an altitude is also drawn from the vertex, but it's not bisecting anything. It's intersecting the other side perpendicularly. The altitude is drawn from a vertex, but doesn't necessarily bisect anything. Don't worry, I'll get rid of this. Bisects anything. Instead, it perpendicularly intersects the side opposite. Well, I won't erase it. I'll just move it down because I want to draw the altitude as well. And I'll label these three. So the altitude would be maybe like in purple here. Let's do like this guy, right? I'm really bad at looking at these things this way. Is that kind of 90 degrees? Pretend like it is. All right, like there. So here we have an altitude. an angle bisector, and then a median. Okay, so like that's the difference between those three. Okay. Number 39, modeling with mathematics. 39. Find the area of the triangular part of the paper airplane wing, I'm 2 hours in, that is outlined in red. Which special segment of the triangle did you use? Okay, this, if you heard me in the lecture portion, if you were in that portion, then you probably saw what I was talking about with respect to a height being perpendicular. Wait, what part's 9? Sorry. Is this entire thing? I'm guessing the entire thing's 9, otherwise they'd label a little part. Anyway, the height is always perpendicular to a base in a triangle. So the triangle in question is the one in red. So we're going to have to determine something there in a bit. I just wanted to mention that to begin with. Okay. What do I want to do? The outline in red, which special segment of the triangle did you use? So what they say this whole thing is 9, I imagine. Therefore, we have, I guess I'll copy and paste this thing over. Therefore, we can divide that thing. They show some congruent parts, and it shows that we can call some parts 4.5 each, dividing it in half. Okay, if that's 9, then this is 4.5 and this is 4.5, like that. Okay. 4.5 is a very specific length of this triangle, and I could, therefore, then refer to it as its base. The base of the triangle I could call 4.5. Now, this only helps me if I know the height of the triangle, but the height must be perpendicular to the base. This height will be 3. The height will be 3, and here's why. Number 1, it's perpendicular to the base. Number 2, it's the distance from the base, by extension, the distance from, it doesn't matter how far away it is, distance from the base, perpendicularly to the vertex opposite the base, opposite that side. So yes, the height is 3 in this way. Height is 3. Now the area of the triangle is 1/2 base times height. I don't know what I just did. It's 1/2 base times height, which is going to be 1/2 of 4.5 times 3. 4.5 times 3 is 13.5, and half of that is 6.75. So 6.75 square inches. Now they asked another question. What was it? Which special segment of the triangle did you use? That one. I don't know if that helps, if that's what they meant. But yeah, the triangle is the one in red. The dotted lines are just abstract figures from that. I have a landline phone ring. I haven't heard that in ages. Unless it's some sort of spammer thing, so I'm just going to let it ring. Sorry if you hear it. Oh, I'm going to take this phone call, actually. Hold on. Okay, sorry about that. Well, not sorry. I just pause it. You get no break. But my landline was being called because I turned my other phone on silent to record this video for you guys. So someone knows my landline number. I finished 39, right? Because I wrote a 40. Okay, number 40. Analyzing relationships. Copy and complete the statement for triangle DEF with centroid K and medians DH, EJ, and FG. It's best that you probably draw something here, so let's go and do that. It doesn't matter if it's like equilateral or whatever. In fact, let's just make it equilateral. I assume it doesn't matter. But I want to label it just so I know what the heck I'm looking at. All right, so D is the center. Oh, wait, hold on. Where am I? Triangle DEF. DEF. Okay. Now, remember, now this triangle is equilateral just because the way that I use the shape, the tool. So remember, in an equilateral triangle, centroid and orthocenter are the same thing. And every median is also a perpendicular bisector and all this other stuff. Now, these aren't going to be perfect. Actually, that's part of the problem, right? Compass construction-wise, I'm not using a compass, so I can't guarantee that this is an exact centroid or anything. Just roughing it out, and that's totally okay. So this is centroid K, but these are medians now, and that's probably pretty accurate. DH, EJ, and FG. All right. So this is all number 40. So part A, EJ equals blankety blankety blank. So they're trying to ask you what's the ratio relationship, how many times bigger or smaller is one to the other. EJ to KJ. EJ is the entire thing. KJ is going to be a smaller portion of it. KJ is 1/3 of EJ. Therefore, 3 KJs makes 1 EJ. That's part A. Part B. I think drawing this is very important. DK is how much of KH. DK is this guy. KH is this guy. These are both of the inner segments within that, right? And so this should be twice, two KHs, right? DK is 2/3 of the thing. KH is 1/3 of the thing. So it's 2 KHs like that. Part C, FG, is how many KFs? FG is the whole thing. KF is just this little guy right here. KF is 2/3 of FG, but FG therefore is 3/2 of KF. Basically opposite reciprocal, that thing. Flip the relationship around. And finally, D. So they're doing relationships that we didn't really talk about as much, at least not in one fell swoop. That's what we get to do together right here. KG compared to FG. KG is is 1/3 that of all of FG. You take all of FG, divide by 3, you just get KG. All right, that was useful. Numbers 41 to 44, I think I'm going to flip to the next page on my binder paper here. In exercises 41 to 44, point D is the centroid of triangle ABC. Use the given information to find the value of X. So I kind of like these questions in the way that we get to use the proportions with algebra. So let's just kind of keep this guy here in case it's useful. I don't know if it will be. Length of BD is 4x plus 5, and BF is 9x. I guess I get to label here now. So BF is 9x, BD is 4x plus 5. Okay, so 4x plus 5, BD is 2/3 of BF. So 4x plus 5 will be 2/3 of 9x. 2/3 of 9x is 6x, so 4x plus 5 is 6x. Subtract 4x from both sides. 5 is 2x, and x looks like it's 5/2. They just say find the value of x. They don't ask you to substitute anything after, so I will not. All right, that is 41. Doesn't look like copying and pasting is really going to help me too much there, or using the figure, so that's okay. Let's just move on. 42. You can see the diagram on the other side. 42. GD is 2x minus 8, and GC is 3x plus 3. Okay. Excuse me. GD, 2x minus 8, GC, 3x plus 3. GD will be 1/3 of GC. GD is 1/3 of GC. Whoops, let's substitute. Therefore, 2x minus 8 is 1/3 of 3x plus 3. Let's kind of distribute that, right? Divide these by 3, you get x plus 1. Subtract x from both sides, add 8 to both sides, you get x equals 9. Good, these questions are a little faster, and with knowledge that we got to already apply. Number 43. AD is 5x, and DE is 3x minus 2. Okay, AD is this guy. DE is the small guy. AD is double DE. AD is double DE's length. That's how that works. AD is double DE. I like to put the time symbol. 5x is double that of 3x minus 2. So 5x equals 6x minus 4. I'm going to subtract 5x from both sides to get x. Add 4 to both sides to get 4. So x is 4. Okay. Last one of that set, 44. df equals 4x minus 1. And bd equals 6x plus 4. Okay. df, that guy. bd, that guy. I think more of the same. bd is double that of df. bd is double df. I hope I didn't write anything wrong in the other ones because they're using the same kind of relationship twice. Maybe they want to force you to say one is half the other. If I can say double, I'm going to go with it. Double 4x minus 1. So I can avoid fractions at all costs, or use of fractions. I don't need them. 8x minus 2. By distributing the 2, let's subtract 6x over, add the 2 over, divide both sides by 2, you get x equals 3. Again, they didn't ask to find any lengths after that. That kind of saves time in the problems, but that'd be it. All right, 45's mathematical connections. Here we go. I'll probably choose next page. 45. Graph the lines on the same coordinate plane. Find the centroid of the triangle formed by their connections. Okay, so these... Are these the lines for the triangle? Find the centroid of the... formed by there. Okay. So we're making the triangle out of these lines. Hold on, something popped up. So we got y sub 1 equals 3x minus 4. Y sub 2 equals 3/4 x plus 5. And y sub 3 equals negative 3/2 x minus 4. I don't think it'll take too long on that. So 3x minus 4 is a rise 3 over 1, like this. I have no idea where they're going to meet up yet, so I'm just going to draw the lines as big as possible. And if you don't mind, I'm going to not draw arrows and stuff, because I'm going to shrink them later to a smaller triangle. Okay, so here's the first line. The second line, 3/4 x plus 5. Here's 5, and here's rise 3. 1, 2, 3, 4. So they intersect right there. So that's good to know. And down here. Good thing about this is when it comes to centroids, it has to do with midpoints. And with midpoints, we need slope. Well, I'm not sure if that matters. No, we don't really need slopes. I kind of use the slope to get a midpoint, but I guess that doesn't matter. Never mind. The third one, negative 3/2 x minus 4. Okay, that intersects right there. So let's just go up 1, 2, 3 over 2. Up 1, 2, 3 over 2. Okay, now we know where that's going to intersect. So I just get to draw that part. I'll shrink the other two after. Okay. So we got y1, y2, and y3. So they intersect there. There. And there. So here's our triangle. Let's find a centroid by finding medians. Medians are midpoints. I guess I kind of plotted some of those before, but I got to count them again. So I assume that, that was the up 3 over 2 here. Here's up 3 over 1, up 3 over 1. I think that's going to be that midpoint. And here is, what was this? Down 3, left 4. 1, 2, 3, 1, 2, 3, 4. 1, 2, 3, 1, 2, 3, 4. Yeah, so here's another midpoint right there. So these are all midpoints, which means I can draw medians for these. I might as well just draw all 3 because I have them. So let's do that. I'm going to get a median here. I'm going to guess it's going to be at 0, 2. A median here. Yep. And a median here. Oh, yeah. That I probably made sense without needing to draw the diagonal one. So, yes, the centroid is going to be at 0, 0, 2. P is at 0, 2. Is that all they wanted? Yep. And I thought there was a part B. I guess not. Number 46. In what types of triangles can a vertex be one of the points of concurrency of the triangle? Explain your reasoning. We've seen them in right triangles. Now, it says one of the points of concurrency. I believe they're referring to among circumcenter, incenter, things like that. So we're talking about right triangles. A right triangle can have a vertex as a point of concurrency for your for the altitudes of the triangle, and therefore be the orthocenter. This is because the altitudes are also the same as the legs. The altitudes of the two of the altitudes would also be the legs of the right triangle. So they intersect. You know, a right triangle has a right angle, and so those altitudes are also the same as those legs. Now, it's only for orthocenter. There is another one. Remember, when you do the circumcenter, you draw perpendicular bisectors, but those are on the triangle, but not on a vertex of the triangle. So it's a little different thing there. All right, number 47. Use the numbers and symbols to write 3 different equations for PE. So this is interesting because I get to kind of like mix and match. I guess I'll cross things out when I'm done. Now, what they show you here are congruent. They don't tell you anything about centroid or anything else, but we get to infer that. So P should be a centroid because these are bisected, so therefore these are medians here. So P is a centroid. That means we have 2/3 of the relation of all that stuff. So we can figure out which one is which that we want. So let's work with PE and compare it to either. Now remember, it only works. PE is only going to be spoken of with AE and AP. Oh, we're only using those 3. Okay. So let's do some different ones. So PE, it's going to be, here's PE. PE is half of AP. I can say that. So 1/2 of AP. I'm going to pause this thing in a second. I have a sound coming out of my computer. Take care. Sorry, I have a faulty hard drive, and it kind of makes a click sound sometimes unless I run something through. It's hard to explain. All right, PE is half of, all right, so use the 1/2. Half of AP. Oh, these pluses and stuff. Oh, this is right, 3 different equations. Oh, dude, I could do a bunch. PE is going to be 1/3 of all of AE. PE is 1/3 of all of AE. So I'm not crossing it out except to say that I kind of already used it for these. I don't know where to use the quarter, meaning I don't think I can use the quarter. And AP is 2/3. The big thing from the theorem, it's 2/3 of AE. So that's 3 equations using at least ratios with these fractions in mind. Now, the minuses and pluses I want to use. Let's just do a couple of those. Let's say AP plus PE equals all of AE, and AE minus the whole thing minus one of the guys. AP is PE, and AE minus PE is AP. So that's pluses and minuses. I think I've kind of used everything with that otherwise. They said create 3, and I made 6. Overachieved. I don't know if there's anything else I can use. I can't use the quarter to my knowledge with that. All right, number 48. There's parts A, B, and C. Use the figure, and let's answer how we see it. Let's see what they're asking. So we got a figure. We got a lot of different things. I can imagine some big things going down. What type of segment is KM? Which point of concurrency lies on KM? So what you notice here is this length is 9 and this length is 9. That makes those two congruent. That makes KM a median. KM is a median because it's going right in the middle there. Which point of concurrency lies on KM? The centroid lies somewhere on there. Lies on KM. There's 48 part A. Part B. What type of segment is Kn? That is an altitude. Kn is an altitude. Which point of concurrency lies on Kn? The orthocenter. The orthocenter lies on Kn. Just don't have enough room to write all that in one line. Part C, probably should type this. Compare the areas of triangle JKM, and KLM. Ooh, I know where this is going. Do you think the areas of the triangles formed by the median of any triangle will always compare this way? Explain your reasoning. I got to see what that last question is asking afterward. It says compare the areas. I don't know if they want me to actually calculate something, as in to find out what H is. I would have ways to speculate on what I could find out what it is, but there's no like real Pythagorean theorem involvement. It's not like this cuts this thing. Sorry, it's not like this altitude cuts this thing in half, and it's not like we know that this length of this thing right here. So they're probably not asking you to actually find the area itself, other than ways that we can write it out, like in terms of H. So, for example, A of triangle JKM, the area of triangle JKM, it does have a height of H. So there's JKM right here. Height is H if we're talking about a base length of 9. So it's 1/2 of 9 times H, which is 9 times H over 2. I mean, that's just what it is. That is a 9. That's not an A. That's a 9. And the area of triangle KLM, we spoke about this a little bit before. Here's KLM. Guess what? It also has a height of H because that is an altitude still. Altitude of this LM, that's an extension of that, but LM is the base length. So 1/2 of 9 times H, which is 9H over 2. Now, listen, there are ways to find out what that H is. I don't know if they're actually asking you to find it, because that's not the point. The point is they are the same area. So they said compare them. They're the same. Doesn't matter that it moved over like that as long as it's 9. It said, do you think the areas of the triangles formed by the median of any triangle will always compare this way? Oh, I see what they're saying. Yeah, because it'll always give you the same base lengths for them. So that's interesting how they said it specific with medians. I guess that makes sense. The areas of triangles formed by the median of any triangle will always be the same because the base lengths will be the same and the heights will be the same. I mean, straightforward. 1/2 area base times height. So really what they're asking, which I'm not saying I didn't connect the dots, but I didn't really show you what we were talking about with this. We found the area of this triangle, and we found that, or not really found it, but we were looking for the area of this triangle and this triangle. It's two different triangles made up within the bigger triangle itself, and those two together kind of do that. Therefore, the triangle of the entire thing is, base times height, 1/2 base times height, 1/2 of 18 times H, which is 9H. And yes, the median does divide into two two triangles of equal area. Okay, I have only a few questions left here. I forget, are we going to 51 or 54? 54. Darn it. I thought we were going to 51. All right, number 49, making an argument. We shall. Your friend claims it is possible for the circumcenter, incenter, centroid, and orthocenter to all be the same point. Do you agree? Explain your reasoning. I'm going to believe that that is true of the equilateral triangle. So I'm going to say it right now and just make sure my explanation makes sense. Yes, this is true of the equilateral triangle. This is because, and now I believe we stated that that was true of the orthocenter and incenter being the same point with perpendicular bisector, angle bisector. This is because in an equilateral triangle, any perpendicular bisector, which is important for circumcenter, circumcenter point of concurrency, angle bisector, which is an in-center point of concurrency. Any point of centroid, median, which is for the case of centroids, and altitude, which is the case of orthocenters, are all the same segment. So, for any, whoa, I tried to get that right. For any point in the equilateral triangle, that's going to be the case. Way to go, friend. All right, 5 more questions. Number 50. Drawing conclusions. The center of gravity of a triangle, the point where a triangle can balance on the tip of the pencil, is one of the 4 points of concurrency. Draw and cut out a large scalene triangle on a piece of cardboard. Which of the 4 points of concurrency is the center of gravity? Explain. I don't have a compass with me here. This is a case of a problem that I need to skip. That I am not able to do it with. If I were to speculate, because I've seen this before, I've done it before. If I were to speculate, I'm guessing it's the centroid. I'm guessing with the way that the medians work and such, I'm guessing it's the centroid. It says one of the 4 points, though. It may be, it could be the in-center. Actually, I don't think it's the in-center. I'm going to look it up because you're probably going to do it. I'm not actually sure which one it is. I haven't seen this since high school, so I don't know, and I'm not cutting it out myself, so. Okay, I looked it up, and it was the centroid. I'm just going to say that. It says explain. I mean, my explanation would be, look, I did it. So, what you would do to, by the way, as far as the center of gravity goes, they tell you the tip of a pencil is like take the piece of paper thing that you have and then, put it on there and which one made it balance. If you did it correctly, then it would be, that one. I'm trying to find the center of gravity of this. Now, the important other question here is, do all triangles therefore have a center of gravity? I guess, because you can always draw medians on them. So yeah, so every triangle can do it. Can every object? No. Okay, there's number 50. Number 51. Prove that a median of an equilateral triangle is also an angle bisector, perpendicular bisector, and altitude. I guess we were getting to this at some point, and now we have to. So this could be a long proof because you have to prove all 3 parts. Maybe we get to all at the same time. It's obviously a CPCTC triangle bit, but it's more so that you get more out of it. So I don't know. There's a lot we have to do. And within it, I feel like I need to draw an equilateral triangle here as well. So, I mean, I do, but I need to have it within reason of what we got here. So, give me a sec as I try and configure this. Let's draw an equilateral triangle. We're going to be given the equilateral triangle and that we have a median. So, I thought I was almost out of the hole, but of course, these last questions can sometimes be pretty long. I guess that's the case here. All right, how much can if I tilt it, that give me more space? A little bit. Does that help my case, drawing it tilted, slanted? Let's just draw it slanted that way. Triangles are allowed to be drawn that way, why not? All right, that looks pretty good. So I have a triangle, A, B, C. It is all equilateral. All right. Got some statements, got some reasons. 1. Triangle ABC is equilateral. That is given. All right, we are going to draw a median within here. I'm going to draw it from B to this new point D. Actually, you know what? Let's just, for the sake of, because I have more room over here, let's draw it from A to D, like that. Why not? So here's some D. Now with that in mind, AD is median of BC, given. All right, with some givens, we can work some things out. I don't know how much this part's going to matter there, that it's congruent to all those, and that it's half of that. I don't think that part necessarily matters, but we are going to then deduce this and all that. Okay, statement 1 is going to lead to statement 3 now. Now, I could have made my statement 3 a statement 2, but I didn't know which way I was going to draw the median yet. So I'm going to say AC is congruent to BC. This is going to be a lot of the same things as before, but now we're going to do every proof within here. That's the definition of equilateral triangle. Now, it's also definition of isosceles triangle, and I could have mentioned segment BC as well. I don't think BC is going to matter as far as a bigger thing. This could have been isosceles. Well, needs to be an angle bisector too. I wonder if, wait, it needs to be the median is also angle bisector, perpendicular bisector, and altitude. I wonder which part would make this required for equilateral triangle only. Oh, the reason why they said equilateral and not isosceles, this would also be true for isosceles. Reason is because you could do this from any point, but they should have even said from it's okay. All right, statement 4, we'll say CD, what I just drew here. CD is congruent to BD. That's the definition of a median. I'm going straight from median to there instead of median to midpoint and all that kind of stuff. That works out. Okay, which means I might also follow the proof they had in the lecture, which I don't know. We'll see. Statement 5, I'm going to state segment AD is congruent to itself by the reflexive property, and we can prove these two triangles congruent by side, side, side. So, reflexive property. I'll almost have more room for these things after. Triangle ACD is congruent to triangle ABD by side, side, side congruence theorem. Okay, now that we're here, we basically need to, all right, I'm going to do the angle bisector one first. Now that the triangles are congruent, these two angles will be congruent here. They correspond to each other in the two triangles. That's triangle CAD and BAD. Triangle CAD is congruent to triangle, to angle BAD, angle, by CPCTC. Therefore, so here's going to be one of the proofs. Therefore, AD bisects angle CAB by definition of bisector. AD bisects angle CAB by definition of angle bisector. Okay, so that's one of them. We got our first one. There's the angle bisector one. Starring it. All right, second one I want to do. Altitude and perpendicular bisector will kind of be at the same time. Statement 2. Let's do the altitude first, then perpendicular bisector will naturally come because we'll have both parts. So for the altitude part, we need to state that these two angles are congruent by CPCTC. That's CDA and BDA. Angle CDA congruent to angle BDA by CPCTC. Now, they mentioned straight up that these were like right angles, or excuse me, that they were supplementary. No, let's see, how did I say it? I would be doing a lot more like this. I'd be saying, because I forget what theorem they used it off of, measure of angle CDA is equal to the measure of angle BDA. This is going to be the long road, just so you know. That's the definition of congruence. Basically saying that you have congruent angles, therefore they have equal measures. Angles CDA and BDA are supplementary. Angle CDA and angle BDA are supplementary. They're a linear pair. That's the definition of linear pair. I don't think I need to identify that they are a linear pair because that's just their construction. That's just how it's drawn. If they're supplementary, then their measures add to 180. So check this out. I'm going to kind of work this out a bigger way. Measure of angle CDA plus, Yes, I'm going the long road on this. I know. BDA. However they did it in the lecture portion, I can't remember. They basically did all these like 6 lines I'm going to do in 1 line or 2. Equals 180. That is the definition of supplementary angles. I'm just kind of showing you how this stuff works out when you do this. Now I'm going to do a substitution. CDA equals BDA as far as measurements go. So I can replace one. Measure of angle BDA plus measure of angle BDA equals 180. That is substitution, property of equality. Now I could have probably straight up just said 2 times the measure of. That's what I'm going to do next here. This is just going to be a super long proof, guys. I'm sorry. This is the parts where, like I said, they probably did this really fast, and I probably should have used that. So sorry. 180. That's simplification. Combine like terms. I don't know how else you want to say that. It's not a property of equality. I just combine like terms. Now measure of angle BDA is 90 degrees. That is division property of equality. Divide both sides by 2. Because the measure of angle CDA equals the measure of angle BDA, then the measure of angle CDA also equals 90 degrees by the transitive property of equality. And therefore measure, this is why they have, so whatever they used was some sort of theorem. They didn't say which one it was. They just, I think they said definition of linear pair and they were good or something like that. Therefore, these are right angles by definition of right angles. Oh my gosh. Sorry about this. If they are right angles, that makes these perpendicular. AD is perpendicular to BC. So sorry about all that. AD is perpendicular to BC by definition of perpendicular lines. Okay, so from here, we can probably just do 2 more statements, 19 and 20. Just 2 more. 19 and 20, and state these other guys. We can do the altitude. That's what an altitude does. It's something that's perpendicular. You probably could have done it from 17. I'm not sure, but 18 is needed for perpendicular bisector. Oh, I didn't mention bisector yet either. AD is altitude of triangle ABC. ABC by definition of altitude. Okay, now we got to go all the way back to statement 2. Statement 2 said that AD was a median of BC. A median is also a bisector. I guess we could... Does that work? Median bisects? I guess that's definition of median still. Fine. I think I'm fine there. So here's the altitude one. The perpendicular bisector comes from that perpendicular portion as well. I guess I'll make the bisector statement and then I'll be good. AD bisects segment BC by definition of bisector. I think we have that in one of 2 ways. We can either do it from the median statement or the DC is congruent to BC thing. That goes all the way there. So those two together make the perpendicular bisector portion of it. Okay, that didn't need to be 20 steps because probably everything from 12 to 17 could have probably been told in 1 step or no steps if they went straight to supplementary and perpendicular with the linear pair bit. So apologies if I went above and beyond kind of the way that a proof would work, but I wanted to show you something as far as using the math to actually connect something back. Mine was complete, that's for sure. All right, number 52. Construct an acute scalene triangle. Find the orthocenter, centroid, and circumcenter. What can you conclude about the 3 points of concurrency? I'm guessing the conclusion is they're all different and they're all inside the triangle. That's going to be a lot to do. So acute scalene triangle, I can make whatever I want. So I'm going to have to make it big enough. Oh, it needs to be acute. I want to make it very, like, as scalene as I can make scalene go, but still make it big enough to make, all that stuff. It's acute. It's scalene. Is that scalene enough? Make this a little bit longer, but then is that isosceles now? Sometimes it's hard to make scalene. Sometimes you just make a triangle and you're like, man, that looks awfully isosceles. Like that. Did I just make it more isosceles? Did I make this more of a right triangle now? I think the more I make it a right triangle, the better. Not exactly a right triangle, but the more I make it a right triangle, the better, because that makes things more scalene, because then I know that one's more like a hypotenuse, and then that can kind of work itself out like that. So I think that's pretty good by my standards. It's acute, it's scalene. I look at that, that's not a right angle, so that's good. All right, A, B, C. Okay. Got a lot to do on these, and I gotta use a compass for it, so not out of the hole yet. Let's do the orthocenter, centroid, and circumcenter. So they didn't ask for an in-center. So no angle bisectors. Perpendicular bisectors, yes. Where do those intersect? And then all that. Now, I'll do this in order. I'll do the orthocenter first. So with an orthocenter, I'm going to have to do perpendicular bisectors of these three, if you remember how that works. So, what's nice about this, what's great about this is the perpendicular bisectors are also going to be, they will intersect at midpoints of these, which will make medians. That's good. So when I draw this thing, I get to use that twice, if you will. This line matters for a perpendicular bisector, but where they intersect is also important for medians. Nice. I like that. So this here, I have to keep that line, but I also have to note where that intersects. So I'm just going to kind of mark that as a point. Let's just call it D, just because I already drew that one. That point's going to matter and be useful. The whole line's going to matter and be useful as well for orthocenter. Let's do another one. Good. It's maybe technically a little less work than necessary. I'm trying to think if there's anything I can use to make altitudes here faster without... Sorry that this is now green. Hopefully you know what I'm doing. I'm doing two arcs that intersect. Boom, there and there, and I'm going to draw that. I'm going to erase the arcs after, but I want these lines. Oh, and I only need to draw two of these, right? I don't need to draw a third, so nice. Okay, these two perpendicular bisectors, this being a perpendicular bisector and perpendicular bisector, I'm going to call this point E, meet at the circumcenter. Sorry, I kept saying orthocenter. I meant circumcenter. I was thinking of orthogonal points. So, that's the circumcenter. I apologize. That's the circumcenter. So this also bisected these, if you remember. These two are congruent. These two are congruent like that. And I'm going to draw something else in a bit. But this is the circumcenter. If you don't recall, the circumcenter is the point that is equidistant to all three vertices. So that, and that are all the same distance from one another. This length, and this length are all the same. Okay, so that is the circumcenter. Now, I'm not going to erase these lines yet. I will in a second. The next thing I can draw pretty immediately from here is the centroid. I'm going to draw a median from C to that guy. Boom. And from B to that guy. Boom. Those are two medians. Where those two medians meet are the... I'm looking at something and wondering if this is going to be true. Are the centroid. What I'm wondering is if are all these points on the same line with A? No, it doesn't really look like it is. Okay, now I can erase those ones. I don't believe I can use those in any sort of way to then talk about the orthocenter. All right, so those are two of the points right there. Now, if you recall, the centroid is also the center of gravity for your triangle. The orthocenter, I don't think I need these points now either. They're just kind of not used. Orthocenter is kind of just its own thing. Orthocenter, let's go from A. I'm trying to rotate this the right way. Let's go from A And let's, maybe I shouldn't go from A. And let's extend out to B's length. Let's find out B's length here. You know what? If I can't get it perfect, how good is that? Oh, that's pretty good. B's length right there, and I'll draw that. So I can draw now a perpendicular bisector of that little guy right there with B. So B, I'm also going to do the same thing over here. Okay, there's the arc. And let's draw that from A out through there, which will make an altitude. So it's not a perpendicular bisector of 2 points of the triangle. It's 1 point and then kind of a made-up constructed point of the triangle. That perpendicular bisector is not a perpendicular bisector of the triangle, but an altitude there. I still need a second one. I forgot about that. So I probably should have extended that A length out here to C. Pretty good. So now from here, let's just do the same thing. Let's do one for B by drawing ourselves this arc, and hopefully you can follow along with what I'm doing, or hopefully you don't have to do this part and you just get to skip right on by. And then, oh, do I just continue? No, I just continue that arc right there. Duh. And this arc right here, and B now has an altitude right here. Okay. And that is, no, I did something wrong. Hold on a second. What did I do wrong here? I needed to do, I'm sorry, where did I draw these arcs from? This arc. So I need to draw from A. Hold on a second. What did I do? Hold on. I messed up. Why would I continue this arc here? This arc from A makes one from B. Oh. Time out. I'm not thinking of this. This arc is not necessary for me. So hopefully you're not following me too much anymore now. I need to draw from another vertex, from another point. All right, from B, let's do that same thing. I apologize. Sometimes I think I know what I'm doing and I forget what kind of thing I'm drawing. All right, let's draw one through A to make A one of the endpoints, make it a little bit easier. Ooh, this is going to be a skinny one. Let's do C. Otherwise, it won't be very precise. Let's do that again. Let's go. A is the closer point. Man. This tool is not very useful for me. Through A and there. Okay, that's pretty skinny as well. So I kind of have a point right here and a point. This is going to be hard to measure. About right there. That's not very precise, but wow. I'm going to have to do what I do. I guess when I made it more like a right triangle, this is the cost of it. Okay, now here's the tough part. I have to shrink this enough so that when these guys intersect, let's see, I need that to intersect with that. Okay, I'm going to draw a point from C. Yeah, the more of a right angle this is, the tougher this is going to look. All right, there we go. Got a point there. Okay, so that is another altitude. That's this altitude right here from C to there. Okay, so that makes this guy here an orthocenter. Sorry about all that. Okay, now they said, what can you conclude about the 3 points concurrency? One, they're all different. Two, they're inside the triangle. I wonder if there's something about them being collinear, because they kind of look it. I don't know if that's true. It's constructed, but, you know, that last part was a little meager. I can never trust my compass things perfectly, but if you look at, I mean, I wonder if there's, I'm going to maybe Google that and see if that's a thing. But if you look at those three, those are pretty collinear right there. I'm going to quickly Google that and ask, are the orthocenter, and notice that they didn't mention incenter. Are the orthocenter, centroid, and circumcenter collinear? The orthocenter, centroid, and circumcenter of any triangle are collinear. Okay, so that's another, that's probably the thing they wanted you to actually conclude, but the other two things are there as well. So as far as conclusions go, they are different points. They are inside the triangle. And they are collinear. Now, I don't know what the proof thing of that is. I'm not going for that. I even speculated it. I wasn't certain. But they are collinear. They don't necessarily draw to any certain point or anything like that, but they are collinear, and that's the last thing they wanted. All right, number 53 is construction. 53 and 54 is a proof. Oh, my goodness. Okay. Follow the steps to construct a 9-point circle. Why is it called a 9-point circle? We're going to construct a large acute scalene triangle. Find the orthocenter and circumcenter. Find the midpoint between... Okay, I'm going to do this. I'm going to take this one I already made. Assume that it's close enough. And let's hope and pray I don't have to use any of the old arcs because I got rid of them. Okay, do this. Find the orthocenter and circumcenter. Do we need the centroid? Look for the word centroid. No, I'm getting rid of the centroid. All right, find the orthocenter and circumcenter. Done. Sorry. Find the midpoint between the orthocenter and circumcenter. Okay, so to do this, we're gonna have to do construction. So we have orthocenter, circumcenter. Let's hope that it's close to accurate as possible. Let's do a compass construction, and let's draw a perpendicular bisector. That'll allow us to find its midpoint. Where's my compass? There it is. I have two compasses now. Okay, let's find... Oh, that line's a little thicker there. I'd like it to be thinner. Huh. There we go, that's there. So the perpendicular bisector would also represent the midpoint. So, boom. Kind of close. I actually don't know how to do this 9-point thing. I've never done it before. So let's see what they want. So there's the midpoint. Find the midpoint between each vertex and the orthocenter. Okay, so we found that guy. So I don't think we need... All right, so there's a point. Okay. Find the midpoint between each vertex and the orthocenter. I'm glad I labeled it. So we need to find the midpoint here. See, we don't often draw these things. I guess here's another relationship with orthocenters and things, that it can help you do something with circles. Nothing actually new. Mathematicians know a lot more than I do, from Greek things and onward. And I'm sorry if you can't see that C. I know that I was doing something else. All right. Midpoints need to be found here. I do not know where we're going with this, I'll be honest. I didn't read ahead. Midpoints, we got to do the same kind of perpendicular bisector stuff. This will take a bit. Trying to see if I can do any arcs together really fast. I don't think so. So an arc there. And an arc there. Fix this guy a little bit more. And this will be a midpoint here-ish. Okay, so there's another midpoint. Bring that down a little bit. Boom. Okay, let's get rid of those. I don't know if I need those labels anyway, but it's not what I meant to erase. So there's another midpoint. This guy's gonna be a small one. I don't know if it's worth kind of doing all the extra work. I'm just gonna draw arcs and make it happen. Arc there, and where do they intersect? Well, see, that thing snaps into action a little differently. It's probably not even gonna be accurate. It's probably better for me to just make my own. All right, so there's another. That does not look like a perpendicular bisector, man. See, that doesn't look accurate. But you know what? The midpoint looks close enough, but it should be a perpendicular bisector. Either way, that's a midpoint. Right there. Anything that's in between is going to be midpoint enough, I'm sure. And then the last one I need... from B to A, or not B to A, B to that point there. That's why I went down like this. Let's shrink that a little bit. Okay, there and there. Let's find where those guys intersect. Perpendicular bisector of this one here. All right, we got that guy, so that is another midpoint, if you will. All right, so we got our 3 midpoints. Where do we go from here? I do wonder. Okay, find the midpoint. Okay, I already did that. Construct a circle. Use the midpoint in step 3 as the center of the circle, and the distance from the center to the midpoint as the side of the triangle as the radius. Use the midpoint in step 3 as the center, and the distance from the center to the midpoint of a side of the triangle's radius. But those are 3 different... What? What does the circumcenter have to do with this? Oh, it was the midpoint between... Hold on. Find the midpoint between each vertex and the orthocenter. Why do I need 3 of them? Use the midpoint in step 3 as the center. Okay, so I'll use that. Boom. And the distance from the center to the midpoint of a side of the triangle. Side of a triangle? I'm confused. Let me pause and read this a couple times. I'm sorry. Okay, so I'm confused in a couple ways. It sounds like they just want us to take, because here's the orthos. Wait, did they say the orthocenter? No, they wanted this one. Sounds like they just said, just take this and make a circle thing around this from a side to something. I don't know. Okay, so I'm not going to do the midpoint thing yet. I'm just going to pretend like, here's what they said. Here's the, oh wait, that's not what they wanted. Okay, I do want a midpoint. They want a midpoint from one of the sides of the triangle. Let's do the large one. So let's draw one. Even though they didn't ask us to draw this in one of the steps. Oh, I'm sure this was probably used to find the they probably assumed you kept this when you found the centroid. We never found a centroid. Oh, perpendicular bisector. You needed it for that. Okay. So they probably assumed that you kept this. Oh, it should be going through that circumcenter though, so something went a little bit differently. Oh well, oh well. I draw what I draw, and that's all that I draw. So, okay. So here's a midpoint, by the way, right? Okay, let's use that. Whatever. I don't even think I need the circumcenter anymore. But let's use that point. Let's draw a circle. Now, this was just one of the points, though, right? I didn't use any of the other points here. Let's use that point. Let's go from this center here to that center there. Go through it and draw a circle around with that. Okay, so the idea was going to be that these points were all going to intersect together. That this, it's not perfect, right? Clearly. But this apparently were all supposed to intersect inside there. And I guess this is also hitting this midpoint. And this is hitting that midpoint. So let's count the points they're talking about. 1, 2, 3, 4, 5. Wait, where did I start? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, that's the 9-point circle. Not all the points are on the circle. Only 6. That's a lot, but only 6 of them are. The 6 midpoints of the things, and then the other 3 that are made to draw that. Pretty cool, I guess. I mean, my things aren't really to scale, but it works out. All right. That's 53. One more, and we're almost at the 3-hour mark. Number 54. Prove the statements in parts A through C. We're going to be given this and prove that. Let's just kind of, I guess I don't have to copy and paste it over. But I need to draw a scalene triangle LMN. Can't get more scalene than that. Actually, that might be a... Doesn't matter if it's acute or not. Okay, so L, M, N. LP and MQ are medians of scalene triangle LMN. So here's a given for which we must draw. LP, where's P? Oh yeah, have to draw it. LP, not to scale. And MQ. clearly not to scale. MQ are medians. Point R is on ray LP such that LP is congruent to PR. Okay. Point R is on it so that LP and PR. So this needs to extend. Like that. So I need, like this can be, R can be right there. I don't know what this proof is going to be about yet. I don't even know how I'm going to write it. So point R is on ray LP such that LP is congruent to PR. Okay. Point S in the same thing. Point S is on MQ such that blah, 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 blah. So let's stretch that out to there. This will be point S. Sorry if this gets in the way of other stuff. So here's S. And we need to extend that outward. Probably. Okay. What do you want? What do you want? Let's see. Prove. Oh, point. Okay, 3 different proofs. NS is congruent to NR. Okay, so we got to kind of draw those as well. I'm just going to say that there is a drawing and that the drawing is given. So prove that these two are congruent here. 1. Is there any reason to assume these are supposed to be collinear? I don't know. They might have to be. I'm not sure. NS and NR are both parallel to LM. Oh, yeah, I guess they are supposed to be collinear. So, okay. This wasn't to scale. Oh, this wasn't scaled because I don't probably have these as perfect medians. So, let's just pretend like that, yeah, that's supposed to happen. It's supposed to be more collinear looking. How does that look? A little better? All right, 2, prove that it's parallel, and 3, prove that R, N, and S are collinear. I guess that was the last thing to prove. Okay, not sure where to go to this with this so much. I'm going to mark some congruency, try and get a thought at where I want to go with this, and then kind of go from there. Now, this next part, I'm going to mark congruent like this. This is congruent to that, and this is congruent to that. Geez, that's a lot. So when it comes to congruence, oh boy, I don't even know where to go with this. It's all about triangle stuff, triangle congruence and CPCTC. So that's the stuff that you'd want to think about when prove that NS is congruent to NR. To prove these are congruent, I want to prove 2 triangles are congruent within that make this so. So I either have this triangle here and, oh, there's no triangle drawn there. L to M, congruence. Boy, I'll have to think about this. I actually have to use the bathroom, so I'm going to pause for that. Okay, I'm back. Okay, the hard part for me, and honestly, I don't know if I'm going to do 2 column proofs, but the hard part for me is looking at things like items and triangles and stuff like that. So the first thing they want you to do is prove segment NS is congruent to segment NR, these things here, whatever, boom, boom, boom. So it's all about finding their triangles congruent, right? But my thing is they don't have triangles that are the same together. So like this triangle will not be shown to be congruent to that triangle in any sort of way that I can see. But I started thinking more about the fact that since they said they're medians, that this is a centroid and maybe about 2/3 of something. I don't think so. The only other thought that I had, and I got to work off of it, is if I can prove that segments, that like this segment is congruent to this one, and I think I can, if I can prove that these 2 segments are congruent, and that then these 2 segments are congruent, then I can use the transitive property. And I think I can do that because what I actually, and I haven't drawn it yet, but what I'm looking at is, are these 2 triangles here? I can do a triangle here with a triangle there and prove that these are congruent and use CPCTC. And then I think I can do the same thing on this other side that also has LM, because these are the specific ones they had. So I had that one, and then I can also do say, these two right here and here. This would be useful because they both use LM. So the green triangles and the purple triangles. Now I can prove them congruent because the way they had things marked, that this is congruent to that, whatever. So I might have to write out the proof. But also what I have are vertical angles. I have vertical angles here, I have vertical angles here, things like that. So okay, I think I'm going to work the first one off that way. I haven't looked at the other two proof things yet, but that's what I got. So imagine we're talking about, I mean, this is the tough part, is dissecting all that, looking at that. So let me actually draw those back so you can see them. Okay, so for part A, sorry, I got to figure out how I want to write this out because I want you to see it. So statements and reasons. So part A, we're going to have statements and reasons. Okay, lots of givens. Blah, 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 given. I think I want to get less into the nitty gritty of this. See markings. See markings. Okay. With the median talk, I have the markings, okay? I hope that's all right. I don't have much more I can really do here. Okay, I want to talk about vertical angles that are congruent. So these two are congruent and these two are congruent, but I have two different triangles to talk about there. So triangle LPM, or angle LPM is congruent to angle RPN. And in the other one, angle LQM and angle NQS. LQM congruent to angle NQS, I think that I said. NQS, those are vertical angles, the vertical angle theorem. Now with all the other markings here, the given ones, the medians, the whatever they told us, now we can use side angle side. I got side angle side with side angle side on purple. And then I have side angle side with side angle side on green. So I can use those same triangle. I think I made them correspond correctly. So I'm going to say those corresponding parts. Triangle LPM is congruent to triangle RPN. And triangle LQM is congruent to triangle NQS. That'll be the side angle side congruence theorem for both of those. Now the next part is showing that both of these have side length LM. LM is going to be congruent to, I need 5 tick marks, to NR and to NS, but separately, right? LM is congruent to NR and LM is congruent to NS by CPCTC. It's two separate ones, but now, and I know I really did statement 1 really shortly. I apologize for that. So now I can say that NR is congruent to NS by the transitive property of congruence. Looks like the Bills one. Property of congruence. Okay, so there's part A. What's part B? Prove that NS and NR are parallel to LM. NS and NR are parallel to LM. Well, they're the same line. Well, we don't know they're the same line yet, but here's LM. I think I can use my triangle congruence proof from before because I can use CPCTC to show the other sets of angles are congruent, such as looking green right now, and look at this angle here, 3 marks, is congruent to this angle here. These are corresponding parts of the congruent triangles. If they're congruent, the converse of the alternate interior angles theorem can hold to be congruent as well. I can use that. I'm going to do the same thing over here with, I'm going to do 4 arc marks, this guy, and this guy. It's a lot of arc marks, I know. But angle, oh my gosh, LMQ, I have to go back and forth, up and down. I'm just going to write it on the same proof, if you don't mind. Okay. Angle LMQ is congruent to, talking about the green one, angle NSQ CPCTC. I'm going to also use the other one. Not GPCTC. Not corresponding parts. Of course not, silly. This might be my longest video. I did not expect that. And angle MLP is congruent to angle NRP. MLP congruent to angle NRP? NRP. Energy. NRP. Also by CPCTC. Now, both of these will confirm that both of these separate sets of lines are parallel. This is the converse of the alternate interior angles theorem. LM is parallel to NR. LM is parallel to NS. Is that what they wanted? Yeah. LM parallel to NR. Oh my gosh. NR. LM is parallel to NS. This is the converse of the alternate interior angles theorem. If alternate interior angles are congruent, then the lines are parallel. That's part B. Part C asks what? R, N, and S are collinear. To be collinear, they need to be on the same line. Well, here's the thing. They're both parallel to the same line. I know that that's a theorem. I'm not going to prove it. I'm just going to say the theorem. Two lines parallel to the same line are parallel to each other. That's true. Am I sinking? Is my chair sinking? Two lines parallel to the same line are parallel to each other. But they both share point N. I don't know how to write that as part of a two-column proof thing. So I'm going to stop the two-column proof part and just write part C for this. This is... I probably could have done it for that last part as well. No, the last part was good. Part B. I mean, this isn't even a paragraph proof I'm going to write, just the way I'm going to say it. Two lines, oh, part C. Two lines parallel to the same line are parallel to each other. This is a way of saying that they both go the same direction to each other. So NR is parallel to NS. However, because they share point N, they cannot be parallel. Therefore, they must be collinear. Because it shows that they go the same direction. Parallel means, however, that they won't intersect if the lines continue forever. These will clearly intersect forever, everywhere, because they are collinear. So that's the thing on my part C. That's how I'm going to kind of end that one, I think. That makes the most sense in how I want to state that. Not part of the two-column proof, but that's where it ends. All right, guys. That's the last problem, and boy, those construction things really take a long time. That'll do it for this one. This is Mr. Robinson. Thank you so much for watching for this section 6.4. The next video that'll come up is for the 6.1 to 6.4 quiz, or kind of the review and quiz that they have. I'm sure that they have one there coming up. So be ready for that. I hope it's not a lot of compass construction. And guys, no lecture and stuff within as well. But that'll do it for this one. Thank you so much for watching. Take care. I will see you in that next one.